Well, welcome to JavaScript, the hard parts. Tonight we are going to cover recursion. I know some of y'all have been to my recursion workshop before. Some of you, this may be first time. How many of you, this is your first time at JavaScript, the hard parts all in together? Wow. All right. We got a lot of new folks. Well, it's nice to see you all. We've had, last week we talked about closures. Tonight we're going to talk about recursion. My favorite. I've been teaching the recursion JavaScript, the hard parts for several years now, almost exclusively. And it is just a lot of fun. I think it's one of the more complex things to wrap your head around when it comes to writing code. But the great thing about it is, and you may not feel this way right now, you may not feel this way right after this workshop, but I promise you, recursion is one of those things that there will be this just like click when you're just like, oh, I get it. And then you're gonna look back on these days where it was such a mind-boggling thing. And you're gonna be like, why did I think that was so complicated? But trust me when I tell you that everyone, no matter what kind of like experience they have coding before, when they first start to learn recursion, it is just a challenging thing to wrap your head around, right? Because it's just a different way of thinking about iteration in code. Tonight, we're going to break it down the best way that we possibly can. Well, the best way that I possibly can. We'll talk through things. We're going to diagram out. We're going to really kind of like try and see what's going on under the hood when we write recursive code. We're going to try and use some like real world analogies to kind of put it all into perspective and help make sense. But that being said, this is a class and we're all here to learn. So if you have questions, please don't hesitate to raise your hand. You can pop up the virtual raise hand there in your chat box. What I would love to do, since we have so many folks here in the room this evening, I want to go around and I'm going to call on maybe 5 or 6 folks at random, just kind of introduce yourself. What I'd love to know is who you are, where you're tuning in from, because the coolest thing to me about the pandemic and kind of like putting our whole world remote is it's really shown the world what software engineers have been doing for a really long time, that we can do this stuff remotely. We can work from anywhere in the world. And since we've done this, since all of our programs have gone remote, we've had folks tuning in from every continent in the world except for Antarctica. So if you know anyone in Antarctica that's looking to do a coding school, we would love to check that box off. But for now, we've got the other 6 continents, or depending on where you live in the world, the 4 or 5 continents, as I've learned that every country seems to teach that there's a different number of continents. I don't know. I learned 7, but maybe I'll leave you all to chat in the chat there if anybody has any different thoughts on how many continents there are out there. But who you are, where you're from, and I'd love to just know kind of like why you decided to hang out with us here in this Zoom room learning about recursion on your precious Thursday evening. So let's start off with Jordan. You want to kick it off for us?
Hey everybody, my name is Jordan. Let's see, so I've actually been working remotely for the past like almost year, so I've kind of been all over the place. Right now I'm in Florida, visiting some family. So, nice weather down here, not too hot yet. And the reason why I'm here, so I am looking to get into a different career. I've been interested in I guess like different aspects of something computer science related, but it wasn't anything that I studied in university. So I studied linguistics and I've been working more in that field for the past several years. But it's something that's very interesting to me. There's just so many different applications, so many things you can do. And Kyle, like you were saying, it does feel like as I'm starting to learn more about it, like, it's like a puzzle. It's something interesting to kind of figure out these kinds of problems. And I just think it would be a good direction to go in, something that there will be a demand for in the future and will be interesting. So trying to learn as much as I can and yeah, meet some cool people and have some fun.
Awesome. Well, we're happy to have you, man. Welcome, Jordan.
Yeah, thanks.
Let's go with Daniel McMullen.
Am I coming through okay?
You sure are.
Awesome. Long story short, high school math teacher, about to finish up this year. I did a coding class in college, really liked it, made a blackjack game, and I'm just getting ready to do a tech interview for you guys. So I figured I would jump in, check some stuff out, do some paired programming, meet some people, just try to, get ready to hopefully get accepted for that June 27th cohort.
Awesome. Well, best of luck. You're in the right place because I can tell you, I can actually promise you that you will need to answer a recursion problem on the technical interview to get into Codesmith. So this is one of those workshops that you're really going to get the benefit from if you're preparing for one of those workshops. Let's go with Jessica Lynn.
Hi, I'm Jessica. I'm from Brooklyn, New York, and I'm currently in the CS Prep Women and Non-Binary cohort, having a really good time, hanging out. I'm actually a photo editor and producer, but I think I'm tired of the celebrity game, so I'm trying to get out of that. You can only do so much on set with celebrities, but I think I just want to create and solve problems. That's what I'm here for.
Well, I think you are in the right place there, Jessica. So best of luck there. How about Caro? Caro? Sorry, you.
Caro is right. Yeah. Hi, everyone. I'm Caro, and I'm in Brooklyn also. I did CS prep about a month ago, and I'm just prepping for one of my interviews. I have an architecture background and love to build things, but it takes way too long. So I'm excited to build things, build software. That would be really fun and cool.
Awesome. Well, we're happy to have you. Welcome aboard. Let's do two more. How about Henry?
Hey guys, my name is Henry Park. I am a South Korean immigrant. Right now I live in Las Vegas, Nevada. So the reason why I wanted to get into coding is because I felt I was so interested in the problem solving and basically the problem solving and to be honest also I have a degree I have a math degree, and then supposedly I was looking for a job as an actuary, which is like a risk analyst in the insurance industry, but I had a hard time finding that job. Plus I wasn't very passionate about actuarial work, but coding, I fell in love with it. When I first started learning about how to code, I got so excited, and then I've been obsessively studying for 12 plus hours every day. And yeah, I'm very much looking forward to the journey I'll be having.
Awesome. Well, you're on the right path, man. It sounds like you have found something that interests you, and that's really what coding is all about. I think it changed my life. I absolutely love solving code. Every single day is a new adventure, and I think that's one of the most exciting things about it. Let's do one more. Let's see, somebody that I don't recognize. How about Lonnie Hernandez?
Hello, my name is Lonnie Hernandez. I'm calling in from Los Angeles, and also doing career shift. I was in nonprofit for a long time, and it was time for a change. And so I just got done with CS prep. Hello, cohort 69B, I see you. And I'm aiming for the July LA immersive, but recursion was definitely needed. So I'm here, excited to learn more.
All right. Well, hopefully by the end of tonight, it'll make a little bit more sense. Hopefully it'll make a lot more sense. But it's, again, for those of y'all that weren't here at the beginning, it's just one of those things, recursion, that it's really challenging for everyone to kind of wrap their head around when they first start learning to code. But I promise you, you may not believe me, but I promise you, there will be that moment when it just kind of clicks and you're like, oh, yeah, this really isn't as complex as my brain was trying to convince me that it was. But tonight, we're going to whiteboard through, we're going to talk through things and hopefully get a little bit closer to that click. But recursion is a fundamental concept in computer science, right? This is not unique to JavaScript, right? It exists in most programming languages out there. So this is not something that you're only going to work on if you're working as a JavaScript engineer. It enables us to write more intuitive, declarative, and maintainable code, right? What does it mean, declarative code? Ryan, what do you think? Ryan Potter, what is it? What do I mean when I say declarative code?
Oh man. So declarative code meaning something that's it's easy to read, it's easy to identify. It's doing what, you're labeling it as, you're labeling it to perform the action in a sense.
You're right on you're right there with it, right? Declarative code is really about describing what we want and not about describing all of the steps that we need to take in order to get there, right? And we're going to talk more about kind of like where that difference is. But I think one of the best kind of like, descriptions that I like to give is when we're writing code, right? When we're writing out functions, we're writing code, we're really just writing out a set of instructions for a computer to follow, right? So you can think of this just like you would write a set of instructions for just about anything, right? If I asked each and every one of you in here to write out the instructions for how to toast a piece of bread, I would get, how many people are in here? 60, something like that, 60 different explanations of how to toast bread. I would probably, hopefully, be able to toast a piece of bread using any of your instructions, but they would all be quite a bit different. There's a lot of different approaches. There's a lot of different ways to write down the same instructions, right? It's the same way with code, right? There's thousands of different solutions. There are ways to write code where we're going to see this evening, which are a bit more imperative, right? Where we literally just kind of like walk through all of the steps. And if we're thinking about how to toast bread, that would be kind of like bringing down every single possible step, like go to pantry, open pantry door, reach inside, grab loaf of bread, undo twist tie, reach in bread bag. You get my point, right? We're going like really kind of like granular. And this is one way to explain things to another person. It's one way to explain things to a computer. But we could also just kind of like get to the point and just kind of more simply take a piece of bread, put it in the toaster, push the button, wait a couple of minutes, you're going to get toast, right? We're really just kind of like describing like, the toast is done once it's popped up out of the toaster. It's really that simple, right? We can do that in just a few steps. We're going to learn tonight how to write code that's more declarative, that kind of tells the computer what we want and not necessarily every single step it needs to take in order to get there. We're going to learn to accomplish the same things with less code. We'll see what the difference is at. But while we're doing that, we're going to reduce the complexity of our iterative code, as I said, by describing what we want more so than how we want to get it. And this will start to make a bit more sense as we go through. So before we jump in, I want to talk about just some principles of JavaScript. Many of you have been working in JavaScript already. Some of you may code in other languages, or you may have been kind of like studying Python or Ruby or something like that, and you're just kind of jumping into JavaScript. So we want to talk about just kind of the fundamentals of JavaScript and really kind of set the tone for how we're going to explain everything that we're going to talk about this evening. So in code, we have a thread of execution, right? So this thread of execution in JavaScript is a single threaded language, which means that it can only be doing one thing at a time. The thread of execution is just kind of how JavaScript is reading through our code. You can think of like, if you're reading a book and you kind of like one of those people that like follows the lines of code with your fingers, this is kind of like the thread of execution, kind of like reading through our code, right? So we have the ability to maneuver through our code from global execution context to local execution context and back, right? And we're going to talk about what all these things are if those terms are like brand new for you as we get through. But whenever we work with code, basically, we're either doing one of two things. We are either creating data or running functionality on that data. So when we create data, we need a place to store it. And that's where our memory comes in. Memory is going to give us a place to store data so that we can run functionality on it later, or just kind of like recall it later on, right? You can think of it just like your own memory. You're like, I need to remember this, right? So you put it someplace where in your brain where you can easily remember that as you need it, right? We're going to do the same thing when we're writing code. We're going to call this our variable environment, right? So this is where we're calling it a variable environment because it's where we're going to store all of our variables, right? Our constants, our variables, anything that we need to store in memory, we're going to put in this kind of like space in memory. We're going to see tonight a couple of different places where that can live, but basically this is a variable environment, right? This is our memory. We are going to really talk about the call stack this evening. And the call stack is going to be integral in our understanding of how recursion works, right? Because we'll get to kind of like how we're going to really dive into the call stack as we get through. You're going to see when we get to the recursive solutions that we're going to whiteboard through this evening. But in JavaScript, as I said, we can only ever be doing one thing at a time. So every time we invoke a function, we're going to push that function onto the call stack. And it's going to create something called a stack frame. That stack frame itself is going to have our variable environment, our local execution context. We're going to have all of these things on the call stack. Whenever we're finished with a function execution, we will pop that call stack, that function off of the call stack. A call stack is a stack variable. It's an instantiation of a stack data structure in JavaScript. A stack is, again, a data structure that exists across many different programming languages, but it works much like a Pringles can, right? So if you think about a Pringles can, if you want to take a Pringle out of the Pringles can, there is no way to get to any Pringle except for the very top one. If you want a Pringle underneath the very top Pringle, you've got to take the top one off first, right? Similarly, if you want to put a Pringle back in the can, there's no way to put it on the bottom. It has to go on the top. A call stack is going to work the exact same way. As we invoke functions, we are going to push that execution onto the call stack. It will go right on the top. We'll always know where we are in our code because we're going to always be in whatever is on top of that call stack. We're going to draw this out tonight. This is all going to make more sense. Whenever we're finished with a function execution, we will pop that off of the call stack and we will move back down to whatever is now on top of the call stack. So basically whatever was underneath that piece. So it works in the way of last in, first out. We're going to draw this many times this evening and kind of see what we're looking at. So this code over here on the right, we have a function multiplied by 2, takes in an argument of n, returns n times 2. Pretty straightforward function. Hopefully, even if you've never seen a line of code before, you can probably kind of make sense what this function multiplied by 2 does. Next, we have a constant output that we're creating, which is then going to invoke multiply by 2 with an argument of 4. We know that we are invoking this function because we see these open and closed parentheses after the name of this function that we have declared here on the first line. So if this is the first time you've ever seen a function declaration or learning how to declare variables, I encourage you to come to our intro to JavaScript workshops that we do on Tuesday night, where we really kind of like take it back to the very first steps of learning to code, where we talk about how to declare variables and how to declare constants, variables, kind of control flow, these different kinds of things. Tonight, we're going to assume that you know a bunch of those things, but if you have questions, again, pop that hand up. This is what we're here for, right? We're here to answer those questions. We're all here to learn about recursion. So I promise you, whatever question you have, probably a few other folks in the room that want to hear the answer to that question as well. So don't be shy. So we are going to start off by whiteboarding through this arguably simple code execution so that we can kind of get an understanding of how we're going to utilize our space this evening. So let me get my board ready here. Ooh. Okay, so to kick off tonight, we're gonna set things up the way that we do at all of our JavaScript the Hard Parts workshops normally, where our entire board here is what we're gonna call our global, can't write with an eraser, global execution context. Now, our global execution context is the space with which all of our code is going to run. This is where JavaScript is going to start reading through, okay, we're declaring a function. Okay, we're creating this constant output. This is where it's going to do all of that for us, right? So we said we're going to have memory in JavaScript, right? So for now, we're going to create a little space over here, and we're going to call this our global memory. It's like our global variable environment, right? Where we're going to store global variables that would be accessible through our entire application. So we also said we're going to have something called a call stack. So we'll draw the call stack over here, our little Pringles can, if you will. This is the call stack, right? Now, as I said, the execution context, right? Whatever functionality we're running at any given time is what's going to be on top of the call stack. So all of our code runs in this global execution context. So for right now, global is going to be the execution context that is on the top of our call stack. It's the only thing in our call stack, right? So global execution will always be at the base of your call stack. Anytime we invoke functions, we will pop them on top of there. We're going to see this more and more as we get through the workshop tonight. So let's kick it off. Alex, will you walk us through this kind of like code sample that we've got here?
Sure. So first, in the global memory, we're going to declare a function labeled multiply by 2 with a parameter of n.
Okay. And what am I going to store in global memory with this?
We'll store the function definition.
And what does that mean, function definition? Like what, if somebody's never heard that term before, like how do I know what a function definition is?
It's pretty much what the function is going to do. So it's going to be the information between the code blocks, or the curly braces, I mean.
Exactly. We're going to take all of this, everything from that open curly brace to that closed curly brace. We're going to store all of that over here in our global memory. Basically, this is that set of instructions, right? And we don't need to do what's in the set of instructions right now. We've just written them down and we're storing them, right? Think of it as like a recipe that we've written down for grandma's meatloaf, and we're storing that over in our recipe box so that we want to make grandma's meatloaf, we can just pull that out and run that set of instructions. So what line do we go to next, Alex?
So next, we're going to skip down to the second to last line, or I guess last line, where it's constant output.
Okay.
And in our global memory, we will declare that constant labeled output.
Okay.
And then it'll be assigned the value of the evaluated expression of the invoked function multiplied by 2 with a parameter, with an argument of 4.
Okay. So if I'm going to invoke this function, right? And I mean, like, I don't have a value for output until I can actually run this functionality, passing in 4 as the number. What am I going to have to do in order to run that code here, Alex?
So we're going to have to enter a local execution context to execute the function.
Okay. And a local execution context is going to look awfully like a global execution context, but it's going to be specific. Oh, we're not going to try that again. To this one function execution. The reason that we get this local execution context, as Alex mentioned, is because we need to push multiply by 2 onto the call stack, right? So anytime we invoke a function, we're going to push that function execution onto the call stack. So when we push multiply by 2 with the argument of 4 onto our call stack, we'll open up this local execution context for us to run that code within, right? So this local execution context here is essentially running this code right here, multiply by 2 with the argument of 4. Chris, question?
Yeah, someone in the chat had a question that I kind of have a question about too. Does the function, where does the parameter go in the global memory there?
So the parameter, this is all kind of just part of the function definition, right? So when we
Okay.
store the function definition, it's basically saying we've created this label, multiply by 2. We've saved this whole kind of like function definition. Here, when we saw in, we're declaring that parameter. It's all stored as part of this function definition in JavaScript or in our global memory or in whatever memory that we actually declare this function in. So that brings me right now, I guess, to the first thing that we do as we've pushed this onto the execution context. We've now opened up this local execution in which to run our code. Alex, what is the first thing I do when I invoke this function now?
We need to pair our argument and parameter.
Yeah.
So
what does that mean? What does that mean?
So the parameter is the item inside the parentheses when the function is first declared. So in this case, the parameter is n. And
oh, I think we lost him. We'll pick up there. So basically, in is our parameter, right? That we created whenever we defined this function. We said in is going to be whatever value we pass in, right? So our argument is the value that we actually pass in that place. So as Alex so eloquently said before he froze, what happens when we invoke a function is we're going to match up our parameters and our arguments, which means the first thing we do whenever we invoke a function is we are going to put that label of in, our parameter, into our local memory and give it the value that we've passed in as the argument. So we're matching up parameter and argument. So in this case, in equals 4 in our local memory. Let's see here. Matthew, you want to jump in where Alex left off there and walk us through these last couple of steps?
Yeah, sure. So did we leave off with declaring n equals 4?
That is correct.
Okay, so if we have matched up the parameter to the argument 4, then within our local execution context, we will have to return n times 2.
Okay, so we're going to return n times 2. And where do I get that value for n?
We're going to first look in local memory.
Do I find it?
Yes.
Okay, so basically we'll take that value. So n is 4. So 4 times 2, obviously 8. Where do I return that to, Matthew?
You will return it to where it was called from.
Okay. And in this case, where was that?
Within your global execution context.
Okay. It's going to return right over here to output, where we invoke this function here, right? So
yes,
we can store 8 as our value and output. And then very important thing to remember here, whenever we return out of a function, Matthew, what happens? What are the two things that are going to happen automatically when we use that return keyword and return that value out?
We will pop off that stack frame from the call stack. And after doing so, it makes this local execution context eligible for garbage collection.
Absolutely. So what that means is once we pop this function, this stack frame off of the call stack, JavaScript's like, oh, okay, cool. I guess you're done with that, right? It's kind of like, you know, when you're a kid and you got your little squeeze box and then you finish it and you throw it on the counter and your mom's like, oh, I guess you're done with that. I'll pick that up and throw it in the trash for you. JavaScript, it's kind of like our mom in this place, and it's going to take the trash out for us when we're like, yep, we're done with that. You don't have to do anything. JavaScript's going to do all that work for you. As soon as you use that return keyword, it will send the value that you had back to wherever you invoked that function. It will pop your stack frame off of the call stack, and it will garbage collect any of that, the variables, all of this stuff, everything that is inside of this local execution is now lost and gone forever. All we hold on to is whatever value we returned out of that execution. So we've got 8 over here. We've popped that off, which means that, as we said, we're always working in whatever execution context is on top of our call stack. So once we pop multiply by 2 with the argument of 4 off the call stack, global is what's left. So we know we're going back into the global execution. Matthew, do we have any more code to run here?
We do not.
We do not. So we have finished this function execution. So let's hear for Alex and Matthew for walking us through that. Nicely done. Nicely done. Can I just get, I know that this is like extremely basic, kind of like coding that we've gone through, but it's really not about understanding the function multiply by 2. It's really about understanding all of the things that we're going to talk about tonight with the global execution context, the stack frame, and all these pieces. So I'd love to just get like thumbs up if you're like totally understand, thumbs down if like I have no idea what you're talking about, sideways thumb if you're like, I kind of have a question. Daniel, you have a question?
No question right now, just in the middle, but
Okay.
I will let you know.
Okay, you let us know and we will definitely help fill those holes in if we can. So we've got this piece done. Let's move into setting up the stage for actually getting to the recursive part of this evening's workshop. So repeating tasks is a critical component of all programming, right? As I said, we have data that we store in memory. We're either creating data or we're running functionality on data. Oftentimes when we're doing that, we are iterating through sets of data. We're iterating through various variables. We're iterating through various like counts, whatever it may be. We're going to kind of see this. Tonight, we are going to walk through this function, sum naturals. We're going to see sum naturals 3 different ways. First, we're going to see it without recursion. Then we're going to see it with 2 different types of recursion. So before we get there, let's talk about like, you know, the more imperative way of explaining to the computer how to sum all the natural numbers below n. So what does that mean? Sum naturals, a natural number is a whole positive integer. So sum naturals is going to essentially take n and it is going to add n plus all the numbers below it. So if we want the sum naturals of 3, we're looking to get 3 plus 2 plus 1. Sum naturals of 4 is 4 plus 3 plus 2 plus 1, and so on through infinity, right? So anytime we're working with iterative code, right? Anytime we're working with any kind of like loop, and as you can see here, we're going to use a while loop here. If you've never seen a while loop before, that usually, you know, for loops, I feel like are kind of like the first loop that you come across when you're learning to code. While loops, they work very similar to a for loop. We're basically going to say, while n is greater than or equal to 1, we're going to continue doing this thing over and over and over again. So it's very important to understand when we're talking about kind of like any kind of like iterative code, whether it's a for loop, a while loop, a for in loop, a for of loop, whatever kind of like loop that you're working with, there's 3 important things. Number 1, initial value. You need some kind of starting point, right? Starting point to start your iteration. Next, we need a breaking condition. We need some way to tell the computer when to stop doing this thing over and over again. What would happen if I don't have a breaking condition? Deepan?
If you don't have a breaking condition, it'll just keep running.
It's just going to keep going forever and ever, right? It's kind of like you need some way to, computers, a lot of people think, you know, computers are super smart. So computers are only as smart as we program them to be, right? We write down the instructions. They're really good at following instructions. They will do exactly what we tell them to do. So if we tell them to start doing something and keep doing it until we tell them to stop, they will keep doing it until we tell them to stop. So if we don't tell them to stop, what we've created here is what we call an infinite loop, which is not something that you ever want to create because it will crash your system. So initial value, starting point, breaking condition, end point, right? So update expression is this 3rd piece. This is how are we going to modify our initial value on each iteration so that we eventually get to that breaking condition, right? If we're trying to count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need to know like how to actually, we need the starting point is 1, the ending point is 10. but we need to know how to actually get from 1 to 10, right? So these three things are important in any kind of iteration. So in this code example over here on the right, Chris, what is the initial value that we're going to use for this loop?
Some naturals.
Well, some naturals is the function.
Oh, 0.
So with this like while loop in here, right? What is the initial value that we're going to use to kind of like be as our starting point for our loop?
In.
In, exactly.
Okay.
So we've got in is our initial value, right? And you can usually, it's usually pretty easy to tell what the initial value is when you look at what the breaking condition is. Josh, what in this equation is the breaking condition?
The breaking condition will be as long as n is greater than or equal to 1.
Exactly. This is our breaking condition, right? So our breaking condition is as soon as n is no longer greater than or equal to 1, we're going to break this loop. We're going to stop, right? So the best way to typically think of like, what is my initial value is, what value are you checking in your breaking condition? That's typically going to be your initial value. When we look at a for loop, right? The very first piece of that for loop is typically like, let I equal 0. I is our initial value in that case, right? Our breaking condition being that second piece, as long as I is less than whatever it is, right? So in a while loop here, our initial value is going to typically be whatever variable it is that we're kind of checking against in our breaking condition. So if n is our initial value, as long as n minus is greater than or equal to 1 is our breaking condition. Jamie, what is the update expression?
Is it not n equals n minus 1?
Man, you guys are on top of it today. I don't remember the last time I did this workshop and I got 3 out of 3 perfect answers here. So kudos to all of you this evening. This is our update expression. And what that means is this is the part of the loop that's going to change the initial value on each iteration so that we eventually get to our breaking condition. So we understand kind of like how this while loop works, what all these different pieces are. Let's draw it out. So here we have some naturals. We've got our global execution context here. We'll abbreviate that. We've got our global memory over here. And let's get that call stack. Good old Pringles can over here on the left. So what was it that I said is always at the base of the call stack, Carl?
The global stack.
The global execution. So the global execution, and that's because all of our code runs in the global, right? So that's where we're starting. That's what's on the base of our call stack. So, Carl, while I have your attention, why don't you, would you mind walking us through kind of like what's happening in this code over here?
Sure. So we're declaring a function, some naturals, and storing it in the global memory, storing the function definition in the global memory.
Okay. What's next?
Then we are going all the way down and declaring a constant output and assigning it the value of the invocation of the function some naturals with the argument 3 passed in.
Okay, so what does that mean? Like, how am I going to actually get that value there, Carl?
So we are going to open a local execution context called some naturals.
Okay. What else?
We'll have a local memory. It will also be pushed onto the call stack.
Exactly. And this is an important thing to remember. because the reason that we get this local execution context is because we push it onto the call stack, right? So as soon as we invoke a function, we push it onto the call stack first. By doing so, it creates this, what we're calling local execution context here for us. So here we have, and as you can see, I am a very lazy engineer, and I am going to abbreviate some naturals to be some nats for the rest of the evening. You'll see why in a few minutes when you see how many times we're going to write some nats tonight. So if you see some nats, we are referring to some naturals. Okay, Carl, we've pushed it on the call stack. We've created this execution context. What's the first thing that we're going to do as we enter this execution context?
Do we bring the thread of execution into the local execution context?
We could definitely do that. Let's have our thread of execution up here. The toe, we'll shorten it as, which starts here in the global execution. As we push some nats onto the call stack, create this local execution context, the thread of execution is going to enter into this local execution. So,
And then, oh, sorry.
no, go ahead.
And then we'll resolve our parameters and arguments.
Right. So we're gonna, and so when we do so, what are we storing in our local memory here?
So in our local memory, we're storing the label n and assigning it a value of 3, the number 3.
Okay. So what's next?
So then now that we're in the function, we are declaring a variable result and assigning it a value of 0 in the local memory.
Okay, result equals 3. Okay. What's next?
And then we have a while loop that's going to run as long as n is greater than or equal to 1.
Okay, you're spot on. I'm gonna pause you there for a second, just because I want to kind of like draw this out a little bit, just in case somebody hasn't ever seen a while loop before. But either way, it's going to help us understand like the steps that are actually kind of like being taken as we go through this process. So whenever we see this while loop, right? First, we've said our initial value is n, right? So while n is greater than or equal to 1, the first thing we're going to do is check if n is greater than or equal to 1. If so, we're going to say result equals result plus n, and n equals n minus 1. At the end of that, we're going to loop back up to step 1 and do it all over again until we hit our breaking condition. So if not, we skip down to step 3 and we will return our result. Right? Okay. Dan, question? You are muted if you're speaking.
Oh, no, I'm good. Sorry.
Oh, no, there we go. I didn't. Oh, sorry. Yeah.
Oh, other. Oh, I'm so sorry.
No worries.
That's okay. Well, I was just wondering, you put result equals 3, isn't it 0 in the local memory?
Sorry, I'm having a little trouble understanding you there.
Oh, sorry. You put result equals 3 in the local memory. Shouldn't it be 0?
Yes. Yes, it should be. Thank you very much.
Let's make sure I didn't miss something.
I probably said to you, I'm guessing that was the same question that you had there, Jamie. Was that? Yes. Okay. Awesome. Yes. So you're both spot on there. Result is 0. As Caro probably said 0, and I just wrote 3. So we're here. We're going to check if n is greater than or equal to 1. If it is, we're going to recalculate result. We're going to recalculate n. We're going to keep looping back up to check again and again and again until n is no longer greater than or equal to 1. And then we will skip down to step number 3 and return result. Thumbs on that? Kind of following kind of like what's happening here? Okay. Okay. Awesome. So let's.
I'm sorry, quick.
Yeah, please.
So I'm pretty sure I know the answer, but just to be safe. In the local memory, that is changing with each iteration, correct?
Yes, and we're gonna
gotcha.
through that
Thank you
for sure. Okay, So let's get Jason. You want to walk us through this piece?
Yeah. Okay, so we're at n equals, you're starting at result. So result equals result plus n, so that's 0 plus 3.
Well, first we have to check, right? We have to check is n greater than or equal to 1, right? So essentially what we're looking at here is 3 greater than or equal to 1?
Yes.
Yes. Okay. So we move to step 2, which is, as you said, take it away.
0 plus 3 will equal result. So result is now equal to 3.
Okay.
And then n will equal n minus 1, which is 3 minus 1, so we equal 2.
Okay. And then what do we do next? What's the next step?
Then loop back up to the breaking condition.
Okay.
And check again. So 2 is still greater than or equal to 1.
Okay.
So we'll execute the while loop again. So result will now equal 3 plus 2. Gosh, which equals 5. And then n equals 2 minus 1, which is 1.
Spot on. Okay, we're getting there. What's next?
Then we loop back up again. And n being 1 is still greater than or equal to 1.
Okay.
So we'll do this again. So result will now equal 5 plus 1, which is 6. And n will equal 1 minus 1, which is 0.
Okay.
And we will then loop back up again, check the breaking conditions. So now it will break out of that while loop.
Okay. So now we'll skip down here. And
yep.
What are we returning out of this function?
So we'll return the value of result, which is 6, to output in global memory.
So we'll store 6 over there. And then once I hit that return keyword and I return 6 over to output, what happens from there, Jason?
The sum naturals function is popped off the call stack, and the local execution context is eligible for garbage collection.
Absolutely. And then if we're following our thread of execution essentially ran all the way through here, pops back out to our global execution. Do we have any more code to run, Jason?
Nope, that's it.
We do not. We have hit the end and we have accomplished our goal. Bam! We just added 3 plus 2 plus 1, and it only took us about 10 minutes to do it. So let's talk about this solution. But before we move on a little bit, just thumbs on just kind of where we're at with these different pieces. Okay, awesome. So let's talk about this approach. Oh, Josh, question.
Yeah, I just had a quick question about while loop syntax. And I first learned it as do while, where you'd use the keyword do, and then the block of code that you wanted to run would be above the while condition. Which way is better in terms of the syntax?
Tomato, tomato. It really is just, again, kind of like we talked about with the toaster example, there's a lot of different ways to explain to the computer how to do the same thing. Right? We could also write this as a for loop, right? There's a lot of different ways that we could kind of use this. So a while loop and a do while loop, they basically do the same thing. The only difference is a do while loop is always going to run at least once because it's going to do the thing and then check. Whereas a while loop is always going to check first before it does anything.
That makes a lot of sense. Thank you.
That's the one kind of like caveat with this. I see do while loops out there, but I've honestly never used one myself. But honestly, I would say I use, if I'm using any kind of like for or while loop, I would use while more than any of those. Anytime I'm using a for loop, I typically am using some kind of method that kind of like creates that for me, like in like practical use. So I'm sure that there are great use cases for do while loops, but I have not personally seen them in like production level code all that often. So if anybody has and wants to leave a comment in the chat about a good use case for a do while loop, we would love to hear about it. But in this case, let's talk about the benefits, right? It got the job done, right? We were able to successfully add 3 + 2 + 1. It's more intuitive for developers who have experience with iteration, right? If you've seen for loops, while loops, it's pretty straightforward how this is working, like what's going on here, right? We're kind of avoiding the complexities of, as we talked about, wrapping your head around recursion, right? We got the job done. Our code is a bit verbose though, right? This is more of like the imperative solution. We're literally kind of going through every single step in order to get to our solution, right? We used 1, 2, 3, 4, 5, 6, 7, 8 lines of code to add up those 3 numbers, right? Let's see what bringing recursion into the mix is going to kind of like do for us. Let's see what it kind of like helps solve in this situation. So what is recursion? Well, before we even go to that, let's see here. Umair, what makes a function recursive? How do I know if a function is recursive just by looking at it?
When it calls itself.
Yeah, when it calls itself within its own function definition. So we said our function definition is everything in between this open curly brace and closed curly brace. So if at some point inside of this function definition, we're invoking that function, we've got ourselves a recursive function. That's all it takes to make a function recursive. So to understand recursion, you must first understand recursion. There's a joke in there. If you don't understand recursion, you probably don't get it. But I encourage you to Google recursion sometime and wait and see how long it takes you to figure out that Google is trolling you in your search results. It's a really fun little game. Google has lots of little Easter eggs, and Googling recursion will give you one of those instances. But as Umair said, a recursive function is one that solves a repetitive problem by calling itself. If we invoke a function inside of a function definition, it is a recursive function. So each function invocation is going to break down the problem into smaller pieces of the same problem. The goal is to break the input down into the smallest possible solution to generate a result. So I can see from the look on a lot of your faces, you're like, that does not help me understand what recursion is. So here's where I like to use my bathroom line analogy of what this first kind of recursion that we're going to talk about is called. It's a linear recursion. So the bathroom line is a perfect example of how to do this. So if you're anything like me, I go to a lot of concerts, music festivals. I'm going to the Beach Life Festival here in Redondo Beach this weekend. Anybody in LA going to festival maybe? Maybe we'll bump in? No? All right. Well, big festival, lots of bands from the 90s, basically my wheelhouse there that I'm very excited about seeing. Out on the beach, people are out in the sun, drinking all day, doing their thing. At some point, you got to go to the bathroom, right? You go to the bathroom at a music festival, there is always a line. I don't care at what time, if it's between sets, at the peak of Daft Punk's like set, whatever it is, there is always a line at the bathroom, right? So, and it's always freaking long, right? It's always long. So you can get there and you may ask yourself, man, how many people are in this line? So, well, there's a couple of ways that you could get this solution, right? I don't recommend trying this at home because you might get like an elbow or you might get some aggro folks at a music festival, but you could jump out of line, right? And just walk all the way to the front of the line, just kind of counting all of the different people, right? Taking, one step forward, count, one step forward, count this person, right? Seems like a lot of work, right? And you've gotten yourself out of line and somebody might start yelling at you to get at the back of the line, and the whole process, it's a mess. You could also tap on the person in front of you in line, say, excuse me, kind bathroom line attendee, would you mind telling me how many people are in front of you in line? And that person's probably going to say, I don't fucking know. And so they're going to tap on the person in front of them. Excuse me, bathroom person line attendee, how many people are in front of you? This is they're gonna, I don't know. And they're gonna ask the question again, right? And this is gonna keep happening until we get to the front of the line. And the person in the front of the line is gonna return back and say, there's nobody, it's just me. I am the front of the line. That person's gonna say, awesome. We're gonna turn around to the person behind them. It's me plus one person in front of me. Cool. That person's gonna say, it's me plus two people in front of me. Great. Me plus three people in front of me, all the way back until you find out that there are 173 people in front of you in the line, and maybe you need to find a tree. So this is kind of an example of recursion, right? We talk about a function invoking itself in its own function definition. You ask the person in front of you how many people are in front of you. That person asks the person in front of them, and this continues to go on until we get to the front of the line. And then the response starts coming back towards us. So let's use that kind of analogy here, and let's see if we can rewrite our sum naturals function to kind of solve itself in a similar way. Before we do, let's understand kind of like the anatomy of a recursive function. So I said when we're working with loops, right? Any kind of like iteration, we needed three things, not the three things that are on the board here, but the three things that we talked about a couple of slides ago. Ryan, what was one of those three things?
We have the initial value.
The initial value. Excellent. Kevin, what is another one of those three things?
The breaking or the condition where it was stop.
The breaking condition. Spot on. Two. Are we going to go 3 for 3 here again? Umair, what's the third thing that we had there?
We have where, sorry?
So we have an initial value when we're using like a loop, like a for loop or a while loop. We have the initial value. We have the breaking condition. What is the third thing that we have to have in every like loop? You remember?
I mean, I was about to say the recursive case, but you're not talking about recursion.
No,
so.
not recursion just yet. It's totally fine. It's totally fine. Darius, what do you think?
Update expression.
The update expression. We got the initial value. So we got the starting point, the ending point, in some way to get from the start to the end, right? When we're working with a recursive function, we're also going to have three things. They're called different things, mostly. They're kind of the same at the same time. So we're going to have, again, our initial value. You can see down here, initial value, right? But in this case, instead of a breaking condition, we're going to have something called a base case. And our base case is kind of it's the most simplest form of our question, right? So in terms of how many people are in front of you on the bathroom line, the base case will be when there's nobody else in front of you, right? When the answer to that question is a simple 0, and we can start kind of like working our way backwards, right? So when it is 0, we can actually return there's nobody in front of us. But if not, then we need to continue asking that question, right? So that brings me to our third piece, the recursive case. And this can be described in smaller occurrences of the same problem, right? So in this case, if we don't know how many people are in front, then we need to ask that question again. We're going to ask it over and over and over again until we get to the front of the line, and then we can start sending that result back. So the recursive case is always where our recursive calling of the function is going to exist. Base case, always going to be the very first thing that we do, right? As we see here, the base case is typically going to be the very first line of a recursive function. The recursive case will be something after that. And it's going to be some kind of conditional, right? We're going to check something. It's kind of like our breaking condition, right? If not, we're going to go into our recursive case. So in terms of this piece, right, we want to ask ourselves, like, how is this task self-similar, right? So this is where I like to think of, let's see here. Let's say sum naturals of 3, right? What we did before. Let's do it here where we have a bit more space. So sum naturals of 3. Well, another way to think about the sum naturals of 3, right? The sum of all numbers below 3 or 3 and below is that it's going to be 3 plus the sum of all natural numbers from 2 down, right? So essentially it's 3 plus sum nats 2. And another way we can think about sum nats 2 is that it's going to be 2 plus the sum of all natural numbers below 1. So 2 plus sum nats 1. That one's going to be 1 plus the sum of all natural numbers for 0, which when we hit to 0, there are no more natural numbers because natural numbers, as we said, are whole positive integers. So that answer is 0. So 0 plus 1 plus 2 plus 3 gives us our answer of 6. So let's see how we can write this out in code, right? How do we get that result? Here, we have our function, sum naturals, takes n as an argument. Our base case, what is the smallest natural number? 1 is our smallest natural number, right? But we need to, what happens if we want to handle for that edge case of what if somebody passes in a negative number? Well, there are no natural numbers below a negative number because a natural number is a whole positive integer. So anything from 0 and below, we're going to return 0 because that will be the sum of all natural numbers below that number. If it's not, then we're going to do exactly kind of what we just drew out here, right? Sum naturals of 3 is 3 plus sum naturals of 2. So the answer to, if we haven't hit our base case, we're going to return n plus sum naturals of n minus 1. Thumbs on kind of like what we're doing here, the logic behind like how this is working. We're going to draw it out, so it's going to make more sense. But any questions before we jump in? Chris, what do you think? Is there anything I can clarify? Or do you think maybe just drawing it out will help?
I think once it's drawn out, it'll help.
All right, well, let's do just that. And if not, then we'll get to some questions right after. So let's, oh, I've got some old code in here. Let's erase all that. Can't be giving away anything here. Spoil the surprise. So here we are. Jeffrey, you got a question?
Yeah. Hey, would you mind for like less than 30 seconds running back up to that 2 slides up? Yeah. Sorry. Just like, okay. Sorry, everybody. Sorry.
Not a problem. This is what we're here for.
Okay,
I see you writing it down. Will these slides be available after the lecture, or is
Yes,
this...
you will all get a copy of the slide deck in your email tomorrow morning.
Okay.
Basically, at whatever email address you signed into tonight's workshop at.
I forgot that I had a cell phone and a screenshot. Sorry, everyone. I'm good. Thank you.
Don't worry about it at all. You won't get the diagramming that we go through, but you will get a copy of the deck, so you can kind of go back through and see all of the steps. So if you want to be able to look back at the diagramming, I encourage you to screenshot that, but I encourage you also to just more try and think through these things tomorrow when you get this deck as you start to go through. So here we have our code, and now we're going to change the game up a little bit here. So we've been talking about, we got our call stack over here, we have our code, and we've been using the whole board as our global execution context. We've been opening up local execution context like kind of on top of that. But as I said before, what's really happening, where we're really running our code is it's all happening on that call stack, right? When we invoke a function, we push something onto the call stack, and that opens up this local execution context. We're going to kind of change the vocabulary we're using around this. We're going to get more kind of like specific on what's really going on here. So when we push something onto the call stack, we open up what we call a stack frame. So whenever we can see this global over here, right? So global pushed on the stack frame means, or pushed on the call stack means that there is a global stack frame, right? So this is like our global execution context. If I push another thing on there, we get another stack frame. Every single function invocation that's on the call stack has its own stack frame. Within that, we have our execution context, right? And that's the execution context for whatever frame we are in on our stack. We have our variable environment, right? We said our memory is just an environment in which we store variables, right? So this is our variable environment. Couple of new pieces that we're going to bring to the puzzle, a couple of new things that we're going to keep track of in each of our stack frames. We have our call site. Now, our global execution context is not going to have a call site. It's the only one that won't, because the global is where our code begins. But as I can't remember who said it before, but somebody said before, when we return out of a function, we're returning it to whatever execution context had invoked that function, right? So as you'll soon see, when we get into recursive functions, there's going to be a lot more on the call stack than we might be used to with our while loop. So it's going to be really important for us to keep track of, hey, who invoked this function? Just so I know, so that whenever I have a value to return, I know where to return it to. So we have this return value space where we're going to write down what value we're going to actually return out once we have one. But our call site is going to be important because it's going to tell us where are we sending that value to whenever we have it. Okay? Questions on just these pieces of the stack frame? Again, we're going to draw this out and hopefully it will make sense. Okay, I see a handful of thumbs. I see a lot of not response, but I'm going to trust that if you're not asking questions, you're following along at this point. So we're going to make this a little bit smaller. And we're going to start with this active context being our global execution. As we said, you know what? I need to copy this. 1 second. Okay, so we're not going to have a call site. We're not going to have a return value for our global execution. It's where all of our code is running. As you'll see, I got it kind of small down here in the corner of the screen. What's also small and down at the corner of the screen, our global execution on the stack frame. So what we're going to do now is we're going to stack our stack frames on top of each other, and we're going to see what's happening in each of those execution contexts the way that it's really happening over here on the call stack. So we're going to look at it that way. This is how we're going to kind of equate that. So let's kick it off. Lonnie, would you mind walking us through this first example here?
Can do. All right. So we have our global setup. So we're declaring function some naturals, passing in the parameter of R, and we're going to store that in our variable environment with the, there we go. Okay. And then we have, okay, sorry. Now we're declaring a constant output, also going in variable environment that is assigned to the value of some naturals, passing in the argument 3. So we're going to open up a local execution context to evaluate that.
Okay, so what we're doing here is we're going to push some naturals with the argument of 3 onto the call stack, right? Anytime we invoke a function, we push it onto the call stack. So we're going to, let's do this. Some nats 3. We're going to push that onto the call stack. And when I do, some nats 3 is going to get its own stack frame. And we're going to basically pop it right on top of global here, just like it looks on the call stack. This is some nats 3. What's the call site for some nats 3, Lonnie?
The global execution.
Global. And how do I know that global is the call site? What do I mean by call site?
It's where the function was invoked.
Exactly. So here, inside the global execution, inside the global stack frame, is where I invoked some nats 3. So whenever I have a return value, that's where I'm going to send it to. So I'm going to keep track of that. I'm just going to write that down right there. So as I go into this execution, Lonnie, what is the first thing I do?
We need to pair our parameters with our arguments.
Okay, so how do I do that?
In our environment, we'll see that looking at the sum naturals, we have n, so that will be our parameter. And we know that they're passing in the number 3 as the argument.
Okay.
Okay, so now we're going to check the condition. If n is less than or equal to 0, it is, or it is not. So we can go to the else return, 3 plus some naturals, n minus 1, so 3 minus 1. And so now we're invoking some naturals passing in argument 2, and we would push that onto the call stack and open another execution context.
So, but I use that return keyword here. I thought like as soon as I use a return, like I'm done. Why am I invoking another function here?
Because we have invoked another function in our return statement. So we need to fully evaluate that before we can return.
Exactly. I can't actually calculate what this return value is until I know what the return value is for some naturals too. So when I invoke that function, we're going to push sumnats2 onto the call stack. We're going to open up another stack frame. This is going to be sumnats2. Now, what's the call site for sumnats2, Lonnie?
It's going to be sumnats3.
Sumnats3. Okay. Do I have a return value yet?
Not yet.
Not yet. Okay. Well, so walk me through what I do next.
So now we're going to pair parameters and arguments again. So n equals 2. We will then check our base case. We do not break that. So now we go to the next state, our recursive case. So now we have 2 plus some naturals passing in 2 minus 1, which is 1. And now we are again invoking some naturals 1, push that to the call stack, open up another local execution context.
Okay. And that is going to give us another stack frame right on top. We're running out of space here. Luckily, our call stack has plenty of space. So here we got sumnats2 or sumnats1. What's the call site for this one?
Call site is sumnats2. We do not have a return value yet.
Okay.
All right. And so we check the pair parameters and arguments, n equals 1. We check the base case. 1 is not less than or equal than 0. So we move on. And now we have n plus, so 1 plus some naturals 1 minus 1, which equals 0. So now again, we're going to push this stack frame onto the call stack, open up another local execution context labeled sumnats0.
Okay. And just for space purposes, we're going to start stacking over here on the right. But just imagine that this is all stacked up above here, right? Use your imagination as we go through this. So this is sumnats0. Okay. What's the call site here?
Is sumnats1.
Okay.
And then we're no return value yet. We're about to check the base case. 0 is equal to 0. So
where do I get 0 from?
Sorry, pair parameters and arguments n equals 0.
There we go.
Check the base case. It does meet that, so we're going to return 0.
Okay, so now I have my first return value. Where do I return it to?
We're going to return it to our call site, sumnats1, and then we can pop off that stack frame sumnats0 off the call stack.
Okay, so we know we're turning it to sumnats1 because luckily we kept track of what the call site was for this function. So we're going to return it to our call site. And you are correct. We're going to pop that off the call stack. This will become eligible for garbage collection. How do I know what call stack, what stack frame I'm going back to after this, Lonnie?
You would look at what's the highest one on the call stack.
Exactly, right? We said at the beginning, JavaScript can only do one thing at a time. So the call stack is going to help us know we're always going to be in whatever execution context is on top of the call stack. So here, sumnats1 is on top of the call stack, so that's where we go back to. And now we have 1 plus 0. We have a return value?
We do. So 1 plus 0, our return value is 1. And we're going to return that to sumnats2. And so we can push, pop sumnats1 off the call stack and return value.
Okay. Keep going. You're on
And
a
now
roll.
we can evaluate this expression now. So 2 + 1 is 3. That's a return value. We will pop off sumnats2 off the call stack. And then the return value goes to sumnats3. And so now we can evaluate that expression. Now we have 3 + 3. So our return value is 6. We're going to pop off sumnats3 off the call stack, and we will return our value 6 to where it was invoked in the first place, output.
And then
we're done.
we are done. It was a trick question. You passed. Well done. Let's hear it for Lonnie there. Amazing job. Amazing job. So let's talk about what we just did here. Let's talk about what we did just here. What's different about this? What are some of the benefits of this versus the previous example that we just worked through? And what are some of the cons of this? What do you think, Matthew? What do you think? What is one of the benefits here?
I think your code is shorter, more concise, easier to read.
You remember what that word was that we said we were going to try and make our code be?
Was it declarative?
Declarative, right? Declarative, right? So we took our code from taking 8 lines of code to get to the solution, and now we've done it in 1, 2, 3 lines of code. We've accomplished the same exact goal, but we used less code to tell the computer how to do that, right? Because we made our code more declarative, right? And we did so by basically just saying, if the number's 0 or below, return 0. Otherwise, return the current in plus in minus 1, right? And we're just kind of we'll just keep doing this. As we said, if it was 100, it would be 100 plus sumnats 99, 99 plus sumnats 98, right? And all the way down. So if we know that that's how we can get to the solution, this is very similar to that bathroom line example, right? It's kind of like, how many people are in front of you? Well, I don't know. I'm going to ask the person in front of me, and we're just going to keep going down the line until we get there. That's just why this is called a linear recursion. Henry, you had your question, your hand up. Did you have a question, or did we answer it already?
Oh, I thought you asked the question, and I wanted to raise my hand to answer it.
Yes. What else is different about this? What is good? What's bad?
Well, I thought since we're putting so many a con of recursion would be we're invoking so many stack frames into the call stack. You might, if the data is sufficiently large enough, it might result in stack overflow, because there's too many stack frames in the call stack.
Stack overflow. How many of you in your searches for how to solve some algo problem that you can't figure out, you Google how to do something and you stumble upon this website called Stack Overflow? Anybody? Yep, we've all been there. Stack Overflow is a great resource. Stack Overflow is referring to exactly what Henry was just talking about, right? But one thing that's different here, right? Well, let's take it a step back. Henry, did we solve this problem even though we have 3 lines of code versus 8 lines of code, right? Did we solve this function any faster or slower this way than we did in the other way?
To my understanding, in JavaScript, because it's single-threaded, I think it takes longer to compute the return value from using recursion compared to a regular for loop.
Actually, no. It's going to actually be the same. It makes sense that you would think that, right? You're like, oh, it's just opening all these things. But really, this is just kind of how it's running these kind of executions in the background, right? So, and when you get to starting to learn about space complexity and time complexity, you'll understand kind of like a little bit more about what these things are, because this is how we measure our algorithms. And I'm not going to dive deep into this because we could do a whole 2.5-hour workshop on time complexity and space complexity. But I encourage you to Google those things and start kind of like understanding this. This is how we measure the efficiency of our algorithms. So in this case, at the end of the day, we still had to add 3 + 2 + 1 + 0. There was no other way around it, right? So we still had to add all 3 of those numbers. So really, it still took the same amount of time as far as like when we talk about like time complexity to solve this. But what we did do here is we took up more space in order to do it. And we talk about our call stack being like a Pringles can. Well, a Pringles can, it can hold a lot of Pringles in a Pringles can. But eventually, if you keep stacking Pringles on top, you're going to run out of space and those Pringles are going to overflow from the can. Very similarly, in JavaScript, we've got this call stack, right? And it's this space in the runtime environment of JavaScript where it is allocated a certain amount of space for stack frames. So the more things we put onto the call stack, the more space it takes up in that call stack. And eventually, and unfortunately, you know, we live in a world where our computers, they only have so much space, right? You may notice this with your phone or your computer. After like a couple of years, start to get a little slower because applications get more complex and your computer doesn't have the memory and the storage space to handle that complexity. This is why things start to slow down, because you're using more of the resources and the computer isn't able to keep up. Similarly, our call stack, it can only hold so much space, right? Depending on how much space we've allocated for that call stack. Once it's full, we have what we call stack overflow, or you will get an error which reads something like maximum call stack size exceeded, which basically means you've overflowed your stack. You've put too many things on there. Now, the good thing is the stack has a lot of space allocated to it, right? We can put somewhere around like 11 or 12,000 stack frames on a call stack in JavaScript, the way that JavaScript is allocated right now. Over time, maybe that will change to be more. Maybe we'll figure out different ways of using JavaScript and it'll be less. But for right now, we have about 11,000. So as long as we are solving some naturals of a number below that, we're never going to have a problem here. But if we start to work with a larger input, like if we want to know some naturals of 100,000, this recursive function is not going to work for us. So we would either have to go back to using that while loop or come up with another kind of recursion, which maybe we'll talk about in just a second. Johnny, you want to, let's take your question.
So on front-end masters, Will Sentence does a course on functional JavaScript.
Okay.
And when he talks about closure, he says one of the advantages is that it allows us to access, lexical scope, to access variables outside of our local, because we can't evaluate expressions as parameters, right? But a lot of recursion is evaluating. So like the sum naturals n-1. So using arithmetic and as a parameter, is that some sort of exception or?
So that's not actually going to be a parameter here, right? So a parameter is like this, right? When we declare a function, we say n. So we're saying whatever number you pass in every time you invoke some naturals, this is what we call a parameter, right? When we actually pass a value in, when we pass in some naturals 1 becomes the argument, right?
That's
so
an argument.
Matching up parameter and argument, we're saying n equals 1. So that's what that is, right? So here, when we're returning, when we return 2 plus some naturals 1, we're not talking about parameters here so much. We're talking about, we have this like mathematical calculation, right? It's the same thing as like saying return 2 plus 3, right? So 2 plus 3, we can actually evaluate that, right? We see 2 plus 3 equals 5. Cool, no problem. But when we say return 2 plus sum naturals 1, we can't actually get a value for that until we run this function and get a return value. So that's why we have to push it onto the call stack. And this is why we kind of like stack all these things on top of each other, because we can't actually finish an execution until we have a full something to return, right? And we can't actually finish that return statement until we finish evaluating that, like, what's the word? Evaluation that we have there, right? So it's like this mathematical equation, right? We have to get both sides of that, right? If we had, as we'll see a little bit later on, if we have two different like functions, we have to first evaluate the first one, and then we can add that return value to the next one. But it's different than closure, right? Because we're not storing anything in like kind of like the, you know, the in a closure, like we would talk about at if you've seen on front end masters, or if you came to the closures workshop last week where we talked the exact same thing that is in the front end masters workshop. Here, the parameters are really just this. We're not storing anything in any secret place. We just can't actually move on from this function execution into the stack frame until we get a return value. And we can't get a return value until we've evaluated another function. That's why we just kind of keep opening them up on top of each other. Does that, I don't know if that.
Yeah, so basically because we've invoked the function already, we're inside the brackets, we can use, that's an argument instead of a parameter.
Yes, so any number that we pass in here is an argument. Yeah.
Okay, gotcha, thank you.
You got it, you got it. Any other questions on this so far? Can I get like thumbs on this kind of like first round? Feel like, okay. I see more thumbs than I saw before, so we must be on to something here. Any other questions before we take a look at another type of recursion, another way that maybe we'll solve that stack overflow problem? I don't know. We'll just have to see. All right, let's take a look. Here we have a function called sum naturals. Maybe you've seen it before. I don't know. But it's a little bit different, this one. Two main things that are different here that I'm looking for. Henry, what do you see that's different about this function versus the previous recursive sum naturals?
Well, first thing I see is that inside the if statement, of the base case, the return value is the variable labeled result instead of, I believe it was 0 prior.
Yeah,
and also
returning 0.
And speaking of the variable labeled result, you initially declare a default parameter labeled result initialized to a value of the number 0.
Oh, the default parameter. Let's write that down. Default parameter. So this is exactly what I was looking for. And Henry already he gave the punchline. He already, it's totally fine. That's what I was looking for. But one of the two major things that's different about this is we have this extra parameter in our sum naturals function, right? We have n as we had before, but now we also have result. But I have this, I'm setting result equal to 0 inside of the parameters, right? That almost seems like silly. Like, what if I'm going to set it to 0 every single time, like, why not just do that inside of the function body? What's going on here? Explain what a default parameter is to me, Henry, or to us.
Default parameter is a variable that you can, well, when you invoke the function, in this case, label sum naturals, you don't have to specify, you can simply pass in one argument at invocation, because the JavaScript will declare a variable labeled result and initialize it to 0. If you pass in additional arguments at invocation, then the result value will change. So sorry.
Yes. No, you're spot on. As you see down here, when I invoke sum naturals, I still only invoke it with the one argument, 3, just like we did before. But you'll see in my recursive case, and this brings up the second thing that's different about this. Before, we were saying n plus some naturals of n minus 1. This time, there's no mathematical calculation here. We're just returning a whole new function invocation. But this time, when I invoke the recursive case, I'm actually passing in two values. I'm passing in n minus 1 in place of n, and I'm passing in result plus n in place of result. So basically, a default parameter works in a way that if I don't provide a value for result, we'll use this value that I've set as 0 by default. So if I don't pass in a value for result, we're going to set result equal to 0 when we match up our parameters and our arguments. But if I do pass in a value, I'll just use that value instead. So it's kind of like, if you give me a value for result, I'll use it. If you don't, I'm just going to set result equal to 0 by default. This is why this is called a default parameter. And we're going to see how this works in just a second. Jamie, question.
So I was just sort of curious. So with the default parameter, are you also able to use like a rest parameter or the spread syntax, or is that not able to be used together at the same time? Or would that ever even be useful?
Yes, you could use, you can use, I don't want to dive, I don't want to go too far off
No,
topic.
no. I was
Going into
just
like
curious.
what rest parameters are and those things, but yes,
Yeah.
you
Yes,
could
okay.
use a rest parameter at any kind of like point in your code. if you want.
Okay, cool.
Cool. Okay. So so this is different, right? Before we were saying like, it made sense. Some naturals, we think about it in that linear recursion way. It's like some naturals is 3 plus some naturals 2. And, all the way down, it made sense as we kind of like drew it out. Well, here we're doing something a little different. Instead of having like a mathematical calculation, we're just kind of, we're keeping result like with us the whole way. We're just kind of like passing it through in the parameters so that once we hit our base case, we don't have to go back. We've already got our answer and we can just return it right there. So let's see how this is going to look, how we're going to draw this out, and how this is going to solve our Stack Overflow issue. First off, this is something called tail call recursion. It's called tail call because the very last thing I do, my final act in my recursive case is to return a whole new function invocation. So at the tail end of this function, I am calling the function again, right? So I'm returning a whole new function execution. This is called a tail call recursion. Jeffrey, question before we draw it out?
Yeah, I just want to make sure that I'm understanding what you said correctly. So, in that previous example, we went sort of like, all the way in sort of like 4, I think it was like 4 or however many execution contexts or, frames that were there. And then we had to return out of each one to come back to the answer. You're saying that this will actually expedite this process because we will go through the same number of execution contexts, but on that final execution context, we will just return our answer out of that innermost one, and thus foregoing the going through and back down to the first.
I don't know. Let's see what happens when we draw it. Let's see what happens. Paul, you have a question?
Yeah, I just wanted some clarity real quick.
Sure.
All the way at the bottom of the code, when we have the uncommented 3 plus 2 plus 1 plus 0, I'm just wondering, like, technically though, since this is a recursion, when ultimately the base case is finally met, then it's actually doing 0 plus 1 plus 2 plus 3, right? In that sequence.
Again, let's see what happens when we draw it out.
Okay.
But essentially, at the end of the day, just like our previous 2 examples, we are still going to have to add 3 plus 2 plus 1 plus 0. There's really no way to get around that. No matter how big our n is, we're still going to have to add up these numbers, right? We're just looking at different ways of going about doing it. But we'll see how it all draws out in when we diagram next. Dan.
Did you say for the tail call recursion, you're returning a brand new function?
Sorry, it's really muffled for some reason.
All right, I don't know. Oh, I have no idea. Am I doing it right? Mike, hold on.
There we go. I was using the wrong mic. Is that better?
That is much better.
Oh, thank goodness. Okay. I was using like the mic for my monitor, which is terrible. Okay. Okay. So you said for the tail call recursion, you're returning a brand new function. Did I catch that right?
We're returning for a tail call instead of before we had that mathematical calculation, right? Like 3 plus some naturals in. Here we're just returning a whole new call.
Oh.
The function.
Okay.
So this is going to change what's happening for us as we draw this out, and let's get to that, and let's see what it looks like.
Okay, cool.
So next up, we've got again our code. We've got our call stack over here. I jumped the gun. I already went ahead and wrote global down there on the bottom. We know what's on the bottom of the call stack by this point in time. So let's just jump right into the code. We've got this is our global execution. Katie, you want to take this one for us?
Sure. So in the first line of code, we are declaring a function sum naturals and storing the function definition that takes in 2 parameters and storing that all into sum naturals.
Okay.
And then we jump down to constant output, where we are declaring a variable, a constant, excuse me, in the global memory called output. And here we are going to equal output to the evaluated expression of the invocation of sum naturals with the parameter or with the argument 3.
Okay, so we've invoked sum naturals 3. What's going to happen here, Katie?
So we're going to go back. Oh, we're going to push sum naturals onto the call stack and open a new local execution context. And here we're going to pair our parameters and arguments. So n is going to equal 3. And because result is not being declared, that is going to be initialized to 0 with the default parameter.
Okay, let me catch up to you there really quick. You're spot on. Everything you said is exactly right. So we've got sum nats 3 that we've kind of pushed onto the call stack here. We've opened up a new stack frame. What is the call site for sum nats 3 here?
It's going to be in global.
Global, exactly, because that's where this function was invocated or invoked, right? Sum naturals 3 happen here in global. So we invoke that stack frame. Whenever we have a result, we're going to push it back to global. So as you said, we're going to match up our parameters and our arguments. What are those values here in this instance, Katie?
So the argument for n is going to equal 3, and there was no result argument passed in, so it's going to go with the default result equals 0. The result will equal 0.
We're going to use that default parameter here, right? So we didn't pass in a value for result, so we're going to use result equals 0 by default. Okay, so we've matched up our parameters and our arguments here. What happens next, Katie?
We're going to go into our conditional if statement, and we're going to see if n, in this case, which is 3, is less than or equal to 0. That is not true, so it's going to jump down to our else statement, and go ahead and return the invocation of some naturals with the first parameter being n-1, which will evaluate to 2, and result
First argument.
argument
Yeah.
n-1, and then the result argument is going to be 0 plus n, which will be 3.
Okay, so here we are going to return some naturals with the arguments 2 and 3. So what happens now? We've invoked another function here, Katie. What's going to happen here?
We're going to push some nats with arguments 2 and 3 onto the call stack and open up another local execution context.
That is exactly what I wanted you to say, Katie, but that is exactly wrong. We've changed the game here. This is where the tail call optimization is going to get triggered, okay? So you're spot on for saying that. It's exactly what I wanted you to say, but this is where things are going to change a little bit. So before, right, we were saying n plus the evaluated result of some naturals n-1. So we can't actually get a return value until we can calculate that mathematical equation, right? So we have to go invoke another function, and then we got to come back, right? And it's a new function with a new set of argument. So in this case, JavaScript says, oh, I see what you're saying. You're saying that some nats 3 is actually the same thing as some nats 2, 3. Because I'm not returning, there's no mathematical calculation here, right? I'm just returning a whole new call to the same function, right? So essentially I'm saying the answer to some naturals 3 is some naturals 2, 3. I'm like, wait, that's the same function I just called, but with different parameters. I did it myself there. Different arguments. The parameters are still in and result. The arguments have changed here. So this is where JavaScript will trigger what is called a tail call optimization. And it's going to say, you know what? Well, I don't need to come back. I don't need to like come back to this like stack frame. Like if you're basically just saying it's the same function, just with different arguments, then I tell you what, I feel like there's a more efficient way of doing this. Why don't we just stay right here where we are and update the arguments that we're working with? And so what JavaScript is going to do is now some naturals 3 on this call stack is just going to become some naturals 2, 3. We're just going to update the same stack frame with new arguments. So we do this here, say 2, 3. It's going to update our in to 2, our result to 3. And we're going to step in and do this again. So I know there's going to be questions, and I'm going to take the questions when we get to the end. So keep your hands up. Katie, keep walking us through now knowing, okay, we're just going to reuse the same stack frame for some naturals 2, 3 now.
Okay.
We've matched up our new arguments with our parameters. So what's next? What do we do now?
So we're going to go down to the condition if statement conditional,
okay,
and take a look at our new argument for n, which is 2. If 2 is less than or equal to 0, it's going, which it is not, it's going to go to the else statement, and then we're going to return the updated arguments of some naturals, which will be 1 and result plus n, which is 5.
Okay. So again, now I've said, okay, the answer to some naturals 2, 3 is some naturals 1, 5. Like, well, okay, Well, I'm already here. Let's just update those. Let's just update those arguments. So let's do that. Let's update them on the call stack here. Has our call site changed at all on this, Katie? We haven't updated our call site at all.
No.
Why not?
I'm not sure.
What did we say our call site was for? What does it tell us?
It tells us where we're going to return our function. Our function, the result of the invocated function.
Yeah. So has that changed?
Not yet.
Yeah, it hasn't. We're still, once we finally have a numerical, well, in this case, numerical return value, we're still going to return it to the global execution context. So that's still where it's going to go. So that's why we haven't updated that piece. But we are going to update our arguments to 1 and 5. So now n equals 1, results equals 5. Okay. What's next, Katie?
Okay, so we're going to go to our if conditional where it says if n is less than or equal to 0. So it's going to look at our one argument is 1 less than or equal to 0. It is not. So it's going to jump to the else statement where we're going to update our arguments in some naturals. So we're going to have n is going to be 0 and result is 6.
Okay, so let's get ourselves all cleaned up here. 0 and 6, 0 and 6, 0 and 6. What now?
So then we're going to go back to our function, some naturals, go down to our if statement, and n now is 0, and it says if 0 is less than or equal to 0, which is true, we're going to return our result, which is currently at 6.
Okay, so we're going to return result, which is, as you said, 6. So now we have a return value. Katie, where am I returning it to?
That's going to be returned to global.
It's going to be returned
and it's going to be stored in the constant output.
Okay, what happens now?
And that is our answer.
It is our answer, but
we're going to push some nats off the call stack, and our execution is going to be eligible for garbage collection.
Spot on, except we're going to pop some naturals off the call stack. We push things on, we pop them off. So this is done. We have evaluated the result. Output equals 6. Again, we have successfully added 3 plus 2 plus 1. Man, we are mathematicians over here tonight. Let's hear it for Katie walking us through that that example there. Well done. What's different here? How is this like more efficient or different? Let's take some questions and kind of like go through it. Daniel.
So answer and ask a question. So my guess was before, it looks like we're working backwards, where before we would sum up 1, then sum 2, work our way. Here we're working our way down. But my question is this how this progression would normally go? Is this something intrinsic in the language to optimize like the compiler or interpreter, whichever one it is? Because it, like I was thinking, oh, we're going to go, to another environment, then run the next one. Is that what's supposed to happen and they've just optimized it?
So basically, yes. And it's great that you said that word optimized, right? Because this actually referred to as it's an optimization that's built into the runtime environment, right? So it's wherever your code is being run, which most JavaScript runs in the browser, because JavaScript it's the language of the front end, right? Unless you're running Node and then your JavaScript is running in Node, in Node's runtime environment. But most JavaScript gets run in a browser. So the browser is the one where that's like our global execution context, the stack frame, everything, it lives inside of this runtime environment, whatever browser is running our JavaScript. So that runtime environment is going to be like, I see that you don't really need to come back to this. There's no mathematical calculation like before, right? There's no need for me to keep this stack frame open and open up another one when I'm really just running the exact same function just with different arguments. So I'm just going to like optimize this a little bit and just stay here in this one. And a lot of folks will ask like, so does it like pop it off and push on a new one all at the same time? And no, it does not. It actually is going to recycle the same stack frame over and over and over again for us. And it's not something we have to tell the runtime environment to do. It's an optimization built into the runtime environment. So it's just going to be triggered automatically when the tail end of our function, when our recursive call returns a whole new call to the same function definition. Because here we're basically said sum naturals 3 is the same thing as sum naturals 2, 3. It's the same thing as sum naturals 1, 5, which is the same thing as sum naturals 0, 6. But when we have 0 as in, we can easily just return that 6. So in this case, I think it's semantics more than anything. But to answer a question, I think it was Paul had asked, we are still kind of adding 3 plus 2 plus 1 as we kind of go through this piece here. Chris, question.
Oh, that pretty much, that little part you just said kind of really answered it, because I was kind of wondering if it was like taking off the stack and putting it on simultaneously. So instead of like a garbage truck coming through, it's a recycling truck coming through.
Yeah. Renew, reuse, recycle. Right? This is what tail call optimization is all about. We're just going to stick, we're like, hey, I've already got this stack frame on the call stack running this function. If you just want me to update the parameters to have different values, I can just do that right here. Why do I need to like open up a whole new stack frame? I'm just going to do that right here. So
and it will do that when there's like not a real like result that has been called yet, or
yeah, exactly. Hokeroy.
I just have two quick questions. I was wondering what triggered this. I guess I know part of the answer, but yeah, what triggered the tail call optimization? Was it just our line, what is it, 5, that one, or was it also the default parameter? So do they go hand in hand, or was it just that line?
The default parameter doesn't actually have anything to do with what's triggering the tail call optimization. The default parameter just allows us to not pass in a value for results so that we can still invoke sum naturals 3 the same way we have every other time, right? The tail call optimization is triggered here when instead of returning this like mathematical calculation, we can't actually return something until we have calculated that mathematical calculation. Here, we're just returning a brand new, like a call to the same function with just different arguments passed in.
I see. Okay. And my follow-up is that I know we can also update these values of n and result outside of the function invocation. So if we just like had it just outside the function invocation, we updated it, would that not make it a tail call recursion anymore? So if we had like, if we reassigned n to n minus 1 and then result to result plus n right above the return statement.
Well, if we did that, right? If we said n equals n minus 1, result equals result plus n, and then ran sum naturals with those numbers, then it would still do the same exact thing, right? We're just adding this logic right into our function invocation, right? So it's going to calculate these numbers here. If we calculated it out here, if I said x equals n minus 1 and y equals result plus n, and I invoked sum naturals xy, it would still pass in those same values, right? So it's just, we're just optimizing our own code by doing that math right here in the invocation of the function.
Yeah, thank you so much.
You got it. Jeffrey.
Yeah, so I think I may understand what just occurred, which is cool. But what I guess I would like further explanation on would be how is it that you got from that first function, like some naturals, like not using, I guess, like how did you get from that function? Maybe it was the first recursive function that you used for some naturals. How did you know? Like, I mean, obviously I know that you know because you know, but I'm saying, how do you get from, this is the while loop. Okay, so sure, even that, right? So how do we get from this while loop to that final, optimized code? It like, but also the one in the middle, the one in between those two. We had one in between them, right?
This one.
This was the first linear, this was like the linear, right?
Yep.
Okay. Is it super annoying to ask if you can like put them next to each other, maybe even all three?
Let's
Is that too much?
Let's
Because it might be.
here. Yes. Okay.
Cool. Thank you so much.
Because I think that's a way to think about this. So let's take this one.
Yeah, I have noticed that I feel like I can almost understand things conceptually decent, but then moving from, let's say something even like, making this for loop and then turning the for loop that you made and using the, for each method, and then from there using the map method and whatnot, sort of like it, that's what this kind of feels like. That's what this kind of feels like. It feels like three.
And this is a great way to look at these, and let's look at them side by side. Okay.
Yeah.
So we've got these three different solutions, right? So let's talk about like the pros and cons of these different solutions, right? So if we go back to what we talked about before, I think it was Henry was saying like that the second solution, like in this first solution, when we whiteboarded it out, we used one stack frame, right? We had our global, and then we invoked our while loop. We used one stack frame. Cool, no problem. We still had to add 3 + 2 + 1. The second time, we came up with a more efficient way of writing the code, right? We wrote it in 3 lines of code instead of 8 lines of code. But this time, I think we had, it's right here, we had 5 stack frames, right? And for every number larger that we're going to add, we would have another stack frame. And eventually, we're going to run out of space in our call stack if the input that we're passing in is too big. So when we think about that, we're like, okay, I need to know the sum of all natural numbers for 100,000. And I know that this solution is not going to work for that, right? So I need to think of a different way to do it. So this solution as well, in addition to the global, only used 1 extra stack frame. So all 3 of these solutions, let me ask you this, Jeffrey. Of these 3 solutions, is any one of them like faster than the other one?
No.
But we skipped, no. They all take the same amount of time, right? In each one of these things, we still have to add up however many numbers it is. If it's 100,000, we got to add all those numbers up one at a time, right? No matter what it is. The beauty of this is, this case, if we're using a large number, right? We have 2 options. We know this one's going to break, right? So we could go back to using the while loop. And there's plenty of times when, even though you might have, how many of you go into like code, anybody on Code Wars? Anybody play around Code Wars? Anybody, you get that solution, you're like, my solution was good, I solved this problem. And then you see some asshole solve that solution with like 1 line of code, and you're just like, man, you throw your computer across the screen. It looks cool to write that 1 line of code, but it doesn't necessarily mean that that one kind of code is more efficient. Quite often it could be less efficient than the 6 or 7 lines of code that you use to solve the same problem, right? As we can see here, there's a lot of different ways to solve any one problem. And as we learn to be engineers, right, it's really about learning as many tools as we have at our disposal. And the more tools we have, and then it's about figuring out, okay, in this instance, what's the right tool for the job, right? I like to refer to this terrible, cheap chair. I make plenty of money. There's no reason why I can't go buy myself a nice chair. It's just the idea of spending $900 on a chair just seems silly to me. So I have this chair that like, you hear it like squeaking. The more I move, the screws on the bottom, they loosen and then they fall to the ground. And like once every couple of weeks, I hear it and I'm like, damn it, gotta pick it up. So there's a couple of things I can do, right? I can pick up the screw with my hand and screw it back in, and I can get it, somewhat tight with my fingers, right? I can grab like, a quarter out of my pocket and I can try and tighten it that way. That might work. I can grab these scissors over here. That might tighten it. But if I have a screwdriver laying around, that's the best tool to use here, right? There might be a lot of ways that I could accomplish my task, right? But the most efficient tool to use to screw a screw into the bottom of my chair is going to be a screwdriver, right? Sometimes I don't have a screwdriver, right? So you make do with whatever you have, right? So the thing about why we're learning about these 3 different ways here, and there's a lot of other ways that we could go about solving this problem, is really just to showcase that there's a lot of different tools that you have at your disposal. And as you're learning software engineering, the more tools that you can learn to put in your tool belt, and recursion is one of those tools that we're learning about tonight, linear recursion and tail call recursion in this case, we're learning a couple of different tools to put in our tool belt, because honestly, I mean, this is a pretty straightforward solution as far as recursion goes. You might still be looking at it like recursion is not straightforward, but once you get that click, this is the most straightforward way of thinking about solving this problem, right? So if we know that our input is not big enough that it's going to break our call stack, right? It's not going to overflow, then this works just fine. But if we know that there's a chance that we're looking for input that's going to be too big, then we're going to have to think of a better way to do that. And that's where we can either think of like a tail call optimization way to do things, or we can just go back to the while loop. There's nothing wrong with a while loop. Really, essentially, we're still doing the same thing under the hood. We're just doing it in a different way, right? So kind of getting from one to the other is really just, like I said before, if I asked all of you to write down how to toast a piece of bread, you'd all write it down a little bit differently. Some of you would have like 10 steps. Some of you would literally have like 2 steps, like put the toaster in the bread, or put the bread in the toaster and push the button, right? So any which way, there's a lot of different ways to do that. And these are just 3 different solutions to the same exact problem that accomplish the same goal. They all take the same amount of time. They're just different tools that we're using here.
Could you highlight, okay, so I guess looking at all 3 of them next to each other, I'm assuming, just by looking, this is assuming that I understand, that there are reoccurring pieces of information across them all. So for instance, I see let result equal 0 on that first solution, and the while, like for the while loop solution, is reoccurs in the as a default parameter. Why did we do that? Because that default parameter is,
because it allows us to still just say sum naturals 3. We want to start with 0 the very first time, like result 0, right? We're starting at 0, right?
Okay.
But you are correct. It's the exact same things. You notice here on every iteration, we update result to be result plus n.
Right.
What do we do over here? When we pass in a new value for result, we say result plus n. We update n to n equals n minus 1. Over here, our first parameter is n.
Yeah.
So every time we invoke the function, we're saying n equals n minus 1. And we're just doing this in a different place, right?
Okay.
We're
And this is standard structure, right?
Yeah, absolutely.
So we would place, I'll be very direct. So when converting, let's say I am going to convert 12 while loops into tail call
optimization.
Tail call optimization.
Okay.
I will place my, the initialization as a default parameter.
Possibly.
I will.
It really just depends on the use case, right? So
okay.
Depending on what problem you're trying to solve, you may kind of arrange things differently. But it's what I want you to grasp here is really just the concept of using recursion to solve the same problem, right? But just thinking about a different way. There is no one just unique, this is how you convert something to recursion, but you can always know that the first thing you need to do is have a base case. It's gonna be the very first thing that you check. And your base case is that smallest thing that you can solve, right? In the linear recursion, it's when you get to the front of the line, there's nobody in front, you have an answer, right? Zero. There are 0 people in front of me in line. Same thing here. Once we get to our n is less than or equal to 0, then we just return whatever that result is that we've kept track of. If the very first number that we invoke is, if we just said down here, some natural 0, well, right off the bat, we would just return 0. And it works, right? No matter what number we pass, that's kind of like how it's kind of keeping track of that.
Okay.
Does that help?
I think so. I'm a huge believer in understanding something conceptually and then going to do it myself and being like, crap.
I promise you, and I promise everyone, I say this after every JavaScript, the hard parts, the best thing that you could do right after this workshop tonight, maybe go take a 5-minute break, come back to your computer, get on CSX or Code Wars or LeetCode, wherever you like to solve problems, and try and solve some problem with recursion, because right now, while we've been talking about it for 2.5 hours, it's fresh on your mind, right? So now is the time, because you can listen to me talk about recursion for hours and hours and hours. If you don't ever actually try and put it to practice, it will never actually get easier to understand. You just kind of have to struggle. We call it block-driven development at Codesmith, right? You hit a block and you're like, how do I solve this problem? And you try things. If it doesn't work, then next time, well, that didn't work. Okay, let's try this. It's the same thing if you play video games, right? You're like, how am I going to beat this boss? You just keep trying different things until something actually works. And then you're like, yes, I finally beat this person, right? Or I solved this shrine in Zelda or whatever it is. It's all like this. You're solving a problem. You try things until something works. And the more you're stuck on things, the more you try, the easier it is the next time you see a similar problem to solve the same thing. But you have to make mistakes, right? As I said, we spend 10% of our time actually writing code, 90% of our time banging our head against the wall, trying to figure out why it doesn't work. And that's a reality right now while you're quote, learning coding, but that will be a reality 20 years from into your career, because you'll always be learning software engineer, because it's constantly evolving and constantly changing.
Cool, thank you.
Can I interrupt real quick? Because I think I understand what Jeff was trying to ask. I think he's trying to say, explain the difference between the three, because we're doing the same one. So what I would explain to him, the one on the left is each time you call a function, you can think of it as taking an action or calling a person, where in the while loop, you're going to step away from the line and do the counting yourself. You have all the information, where in the second one, that's where you're going to make your call ahead to the person in line. Hey, how many in front? Oh, then that person. Oh, hey, how many in front? Till you work your way. Then they're going to report back. And then my analogy for the last one would be, you're going to walk in front of a person, count how many before and in front, then just do that over and over again until you have, okay, I have my sum and then I have my 0, how many people I have to jump in front of. Or maybe I made it worse.
I'm with you on the first two analogies. The third one, I think.
Yes, sorry.
I think really is just JavaScript's way of optimizing the amount of space it takes up to do that second one. So there's not as there's not as much of, I would say, a real world analogy for this third one. It's just the computer's way of saying, you know what, I could do this in a more efficient manner, and I'm just going to do that for you.
2 out of 3 is not bad. I'm going to mute myself now.
They called in a drone.
I like walking through it.
Called in a drone, and the drone calculated the space that people take up.
Okay.
And the length away from you.
I like it. I like it. We'll have a drone. Henry, did you still have a question, man?
I'm good.
You're good. Okay. Ryan.
Yeah, really quick. I was just wondering if you could just reiterate just one more time, what triggers the tail call? Again, I know it's obviously the return line, but
totally fine.
Yeah.
The tail call is returned by this last, like what we're returning. We're not returning a mathematical calculation. We're not returning a number. We're returning a whole brand new call to the exact same function that we're inside of, just passing in different arguments.
So it's a whole brand new call. Okay.
Yep.
A whole. Okay. Thank you.
Got it. Paul.
Oh, so for the second one, it's is the logic still the same on the uncommented where it's doing 3 + 2 + 1 + 0, or is it doing the opposite? Since when we're hitting the base case, we're actually adding it from 0 to 1 to 2 to 3.
So these comments down here are not to say like necessarily the order of which these things happen, right? They're just literally trying to say that at the end of the day, we are adding 3 + 2 + 1 + 0. So don't think of these comments more as like an order of operations so much as just like, we're still doing the exact same thing, right? We're still adding up all these numbers, just kind of in a different way. Because realistically, like our tail call optimization, we're kind of going 0 + 3 + 2 + 1, right? If you wanted to get like semantic about it, but that's not important in this case, right? I don't want you to get like lost in that sauce. These comments are just there just to show you that we're still adding up these numbers. We haven't come up with some like magic formula to calculate this. We still have to actually add these numbers up.
Okay. I
Cool.
appreciate that. Thank you.
You got it. Katie.
Hi, sorry. So I don't know if you touched on this already, but I'm still not understanding. So you said that this is 3 different ways to do the same thing and they take the same amount of time, but why wouldn't we want to do the third way all the time? Or why wouldn't we want to do the third way all the time if we are using less memory or less like call stack?
Well,
is it because we don't ever really reach the maximum call stack?
It really just depends on your use case, right? So there's a lot of reasons why we would write code in any one specific way, right? There's first off, the efficiency of the code. And second off, something that's also extremely important when we're writing code is that it's easy to read and understand, right? And this is like, kind of goes back to those like code wars, like one-liners, right? When you look at it, you're like, what the hell is happening here? And it takes you forever to actually kind of like figure out what's going on. But like when you've got it kind of like mapped out in like multiple steps, it's easier to kind of like follow, right? This is why it's really important to write code that is easy for whoever's coming along after you to also understand that code, right? And it's so when we're writing code for the engineer that's going to come along after us and iterate on that code, right? When you're working on large code bases, they exist for years and years and years. They just continue to morph and change and this, that, and the other. So the code that you write should be as easy as possible for the next person along to like make sense of it, right? Without having to spend a lot of time. Now there's a lot of ways to do that, right? We add comments into the code to explain kind of like what's happening here, right? This is something really, really important. There's a podcast that I absolutely love. It's like my favorite podcast. It has nothing to do with JavaScript, but everything to do with computers. It's called Darknet Diaries. And it's all about, it's like hacker stories, right? If anybody's never listened, if you're into like hacking and security space, it's great podcast. but they actually had a joke on there today. And the joke was, how do you know if you're doing code review, how do you know if somebody's written bad code? And the response was, no comment. Because if your code isn't filled with comments explaining what the code is doing to the next person that comes along and reads it, then it's bad code, right? So when you think about that, right, there's lots of different ways to solve a problem, right? You want to solve it in the most efficient way possible that is the easiest for the next person to come along to like make sense of and not have to be like, wait, what's going on here? Kind of like go through those different things, right? So there's really a use case for all three of these kind of situations. And it really just depends on what you're doing at any given time as to like why you might want to use one or the other. But if you are writing code because you need to write something a bit more complex because you need it for efficiency purposes, it would be really important in something you would want to do to add some comments in there just to explain what the code is doing. So the next person that comes along can just read your comments and understand what's happening instead of having to diagram all through this to like figure out exactly what's going on. Does that kind of answer your question?
Totally. Thank you so much.
You got it. Bobby.
Yeah, conceptually, like the third example with the tail call, in terms of like the bathroom analogy, isn't it kind of like you tap the person in front of you, give them your cell phone number, say, I'm person 0, please add 1 past cell phone number and your tally to the next person, and then magically they text, when it gets the person at the front, they text you back the total.
I'm gonna go with that. I feel like that's kind of like Jeffrey's drone example, right? We're just like, we're giving you a way to like send that back to us whenever you have it. I like it. I might use that, Bobby. I'm gonna steal that.
And then I encountered trees for the first time today and this kind of stuff. Can you use this to like build or search a tree? Tail call recursion.
I tell you what, well, I'll tell you right now, anytime you're working with data structures like trees or linked lists specifically, I can tell you pretty much exclusively, anytime you are iterating through any kind of binary search tree or tree, and for those of you that are like, whoa, what the hell is all this stuff? Don't worry, this is something you'll get to and you'll learn about different data structures, but you will almost always use recursion as the most efficient way to navigate through any kind of tree data structure for sure.
Thanks.
You got it. Okay, which actually brings me to the last thing that we're going to talk about tonight, which is a tree recursion, which is a little bit different than iterating through a tree, but we're going to see why this type of recursion that we're going to talk about is called a tree recursion. So what happens, and don't worry, we're done with some naturals. We've moved on. Some naturals is behind us. We're going to talk about a different function this time around. So what happens when we call a function twice inside of itself? As we said before, the base case is always the very first line of code. Well, over here, we have 2 base cases, and we have 2 recursive invocations of this function. I didn't even think about that. What's going to happen? How is this going to work? Ryan, did you have a question before we jump in?
Yeah, sorry. I literally just want to say I'm so happy we're going over this. This was literally going to be my next question, and I was even going to use Fibonacci as the example because I'm just like, what the heck? This just made my night. I just want to say that.
In for a treat there, Ryan. So here we are. We've got Fibonacci, and most of you, well, some of you in the room might be going, Kyle, what the hell is Fibonacci? Some naturals, that makes sense. What is this Fibonacci thing? Well, if you haven't been in like junior high math in the recent time, you probably don't remember what the Fibonacci sequence is, but I promise you at some point in your life, you were taught this sequence. And it is an infinite series of numbers that starts with 0 and 1. And then every number in the sequence after that is the sum of the 2 numbers before it. It's that simple. 1 equals 0 plus 1. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13, and so on, right? Until infinity. So this is a perfect use case for recursion, because if I want to know the 40th Fibonacci number, I know that it's going to be the 38th Fibonacci number plus the 39th Fibonacci number, right? It's always going to be the two numbers before it summed up. So here we have, and this is just, again, do you care about Fibonacci in your daily life? Probably not, but it is a fantastic way to explain this type of recursion, and pretty much any set of recursion problems that you go and find on the internet is probably going to have some iteration of the Fibonacci sequence inside of it. So let's take a look and figure this out. So the 0th Fibonacci number, like the beginning, is 0 and 1. These are the only two givens. After that, whatever number we go to is going to be the sum of the two numbers before this. So let's see what's going to happen to our call stack. Let's see how this is going to work. Like I have two base cases. I got two things I got to check. I've got two things I got to keep track of. Let's talk through this. And Ryan, since you were so excited about Fibonacci, we're gonna put you in the hot seat here, and we're gonna have you navigate us through this problem here. So he's like, I'm never asking a question again.
Okay, I'm ready to learn.
We got our global here. We got global in the bottom of the call stack. You know what? I forgot. Let's do this first because we're gonna need to copy and paste these. Let's copy that. And now we'll put global back in here. Okay. Before we just even start talking about what's going to happen, let's just draw it out so that we can just see it, right? Because it makes more sense when we can see it, and then we can talk about it afterwards. So Ryan, kick us off here, man. What is going to be the first thing that's going to happen as we start navigating through this code?
All right, we have a function declaration labeled Fibonacci, and that is just going to store the function definition. And then we bypass the function definition, and then we are declaring a constant variable output, which is assigned the evaluated result of invoking Fibonacci with the argument 4.
Okay, so Fib4 is how we're kicking this off. We've invoked Fibonacci 4. What happens?
We're pushing it onto the call stack.
Okay.
And then we are creating a new local execution context.
What's the call site for Fib4?
Call site for Fib4 is global.
Global. Okay.
That is where we were invoking the function from.
Okay. So walk me through Fib4.
Beautiful. So for Fib4, first things first, we pair our arguments with our parameters. So n is just taking on the value of 4.
Okay.
And then we have some conditionals, and we're basically stating if n strictly equals 0, we're going to return 0.
Does it?
It does not.
Okay.
And then if n strictly equals 1, return 1. That too does not. So
Okay.
then we're just returning the invocation of Fibonacci with the new argument n minus 1, which is 2.
Is it?
Oh, wait. I'm sorry, which is 3.
Okay.
Thank you.
Plus.
Plus invocating Fibonacci again with the new argument, which is now 2.
Okay. N minus 2, yeah. Fibonacci n minus 1, Fibonacci n minus 2. So Fibonacci 3 plus Fibonacci 2. Okay. I've got 2 different calls here. How do I handle this?
That is what I've been wondering.
Okay. Well, let's go back to our first example, right?
Yep.
First, we said sum naturals n was n plus sum naturals n minus 1, right? So n we had, so we could move on to the other. Well, here we have two different values that we need. We need Fibonacci 3 and we need Fibonacci 2. So what do you think we're going to do first?
So I think we're gonna pair our first arguments with our parameter. So I think we're gonna take 3 and pair that with n first.
And by that, you mean we're going to evaluate Fibonacci 3 before we move on. Because
Yes, exactly.
and this is how that kind of like mathematical calculation thing works. When we invoke Fibonacci 3 in the beginning of this piece here, right? We can't move on to the next piece of that mathematical equation until we actually have a number here. So first we have to run and get a value for Fibonacci 3, then we can move on to Fibonacci 2. So let's do just that. We've invoked Fibonacci 3, Ryan. What happens now? How do we handle
Beautiful. So we we push Fibonacci 3 onto the call stack.
Okay.
We create a new local execution context. The call site is coming from Fibonacci 4.
Okay.
And then fantastic. Now we're pairing our arguments with our parameters.
Okay.
So 3 equals 3, fantastic. And then now we're just running the code. If n strictly equals 0, which it does not, we're not going to worry about it. If n strictly equals 1, it does not, not going to worry about it. So then we're just going to return Fibonacci with the new argument 3 minus 1, which is now 2. But
Okay.
then do we account for the next invocation?
Well, you tell me. What are we going to do first? What did we do last time?
Well, I think we would still write it out. So we would just say plus Fibonacci 3 minus 2 is now 1, takes on a new argument, but I don't think we would invoke that one yet first. So we write that out, that's included. We're just invoking our first Fibonacci with the argument of 2.
Okay.
So doing so, that gets pushed onto the call stack, create a new local execution context. The call site is coming from Fibonacci 3. Fantastic. We're pairing our arguments with our parameters. And basically n equals 2 now. It does not do anything with our conditionals. So now we're just returning Fibonacci 2 minus 1, which is 1, plus Fibonacci 2 minus 2 is 0.
Okay.
Fantastic. We have another invocation, new Fibonacci with the argument of 1. So push that onto the call stack. Fantastic. New local execution context. Wonderful. And then call site is coming from Fibonacci 2. Pair our arguments with our parameters. N equals 1. We go through our conditionals. N does not strictly equal 0, but it does indeed strictly equals 1. So we're going to return 1.
Okay.
And then that, gets put to our return value.
So we have our first return value. Where are we returning it to?
We're returning that to Fibonacci with the argument of 2. The call stack underneath it.
So here we can say, awesome, we have a value for Fibonacci 1. Great.
Yep.
What happens to Fibonacci 1 here?
We pop that off the call stack. That gets garbage collected. And then oops, sorry, I got a little lost, I guess.
Take your time, you got it.
Wait, so return, okay.
How do we always know what, so when we pop something off the call stack, how do we know what execution we're going back to?
We just refer to the next stack frame below.
It's always whatever's on top of the call stack. So if Fibonacci 2 is on top of the call stack, let's go back over here. We've got that value for the first half of this mathematical calculation.
Yep.
So now we get to move to the other side of that calculation. So now we have Fibonacci 0.
Oh, okay. So now we invoke Fibonacci 0. We push that onto the call stack. We create a new local execution context. Beautiful. Our call site this time is coming from Fibonacci 2.
Okay.
And then now pairing our arguments with our parameters. and n equals 0. We go through our conditionals. This checks out to be true. So now we're returning 0. So we have our other value. That value passes to Fibonacci 2 underneath Fibonacci 0. Fantastic. So now we have our two values. Okay. Great. So that pops off the call stack.
Okay.
Garbage collect Fibonacci 0.
Okay.
And I think we're at a point where we can pass both values down to our next stack frame, Fibonacci 3.
Yeah, we can actually calculate that number now, right? We have 1 and we have 0. So we can say 1 plus 0 equals
1. Oh, beautiful.
1.
Okay. Yes, 1.
We have that value. We have finished calculating Fibonacci 2. Awesome. Where do we return that value to? Ryan?
We return that to Fibonacci 3.
Okay. So we'll put that over there.
Beautiful.
We're done with Fibonacci 2. What happens to that?
So now we need to account for evaluating Fibonacci 1.
But before we get there, we've returned out of Fibonacci 2. So what happens to Fibonacci 2?
Pop off the call stack.
Exactly.
Garbage collect the local execution context.
Okay.
Fantastic. And now we're at a point where we can evaluate the invocation of Fibonacci 1. So by doing so, we're going to push Fibonacci 1 onto the call stack.
Yep.
We're going to create a new local execution context.
Okay.
We're going to pair our new arguments with our parameters.
Can I not just use, I already did this once. Do I have to do it again?
No, you shouldn't have to.
Oh,
So we're just returning 1.
Well, I shouldn't have to. It would be really nice if I didn't have to. But remember, even though we can see it on the screen, this has been garbage collected. It is lost and gone forever. So we're going to have to do it again. So we're going to go through those motions. So Fibonacci 1, what's the call site for Fibonacci 1 this time?
Okay, so the call site for Fibonacci 1 is Fibonacci 3.
Okay.
We are pairing our arguments with our parameters, n equals 1.
Okay.
Fantastic. We're going through our conditionals. It does not evaluate to true for the first one, but it does for anyways. Yes, 1 strictly equals 1. Fantastic. We pop that off the call stack. Sorry, we return the value back to Fibonacci 3.
Okay.
We pop that off the call stack, garbage collect Fibonacci 1, and then we evaluate our two values, 1 plus 1, which is now 2. That becomes our new return value in Fibonacci 3.
Okay.
My God. All right.
We're almost
Fantastic.
done, right? We're almost done, right?
We're almost done. For the
Almost
visual
done.
learners out there, though, dang, this is this is crazy. Okay, so then we have our new return value. That return value gets passed into Fibonacci 4 under Fibonacci 3, correct?
Okay.
Fantastic. So now we have to account for Fibonacci 2. So we have to invoke that. Oh, my bad. Pop that off. Garbage collect Fibonacci 3.
Okay.
Awesome. And then now we can invoke Fibonacci 2. That gets pushed onto the call stack, new local execution context.
All right. You're doing great, man. You're doing great. What's our call site here?
Beautiful. Call site is Fibonacci 4.
Okay.
And then we are pairing our new parameters and arguments. So we are taking on n equals 4. I'm sorry, n equals 2. N equals 2. Thank you.
I was gonna say,
Yep. Oh my gosh, what is about to happen here? Okay, so it does not.
Thought we were almost done, but
right.
we're getting there. We're getting there.
It does not evaluate to true for either of the conditionals. So now we're returning the invocation of Fibonacci. Beautiful. 2 minus 1 is 1. 2 minus 2 is 0.
Okay. And then
Okay. So
you got it. It's the exact same thing that we've been doing. So we've got Fibonacci 1 plus Fibonacci 0. So,
yeah, so now we need to invoke Fibonacci 1.
Okay.
Okay, great.
Push that onto the call stack.
Put onto the call stack
frame.
Yep. Okay, awesome. The call site is coming from Fibonacci 2.
Okay.
We're pairing our arguments with our parameters. So n equals 2. Going through the conditionals, it does not evaluate true for either of them. So now we're returning Fibonacci.
Which
Oh, I'm sorry.
Yeah.
Yes. So it does evaluate true to n strictly equals 1. So we're returning 1.
Okay.
Beautiful.
Where do we return to?
We are returning that to Fibonacci 2.
Okay.
And then we pop that off the call stack, garbage collect that local execution context.
Okay.
Beautiful. And then now we account for the invocation of Fibonacci 0. So we push that to the call stack, create a new local execution context. Fantastic. Fibonacci 0. Call site is coming from Fibonacci 2. Pair our arguments and our parameters. So n now equals 0. Fantastic. That does evaluate true. So we're going to return 0. That gets passed back to our return value, Fibonacci 2. And then we pop that off the call stack, garbage collect Fibonacci 0.
Okay.
And now we evaluate Fibonacci 2. We have the values 1 plus 0 is 1. Fantastic. That gets returned to Fibonacci 4.
Okay.
Under Fibonacci 2. Fantastic. And then now we can evaluate those two values, 2 plus 1 equals 3.
But first,
oh, sorry. First, yep, pop that off, garbage collect, and then we can evaluate those values. And then we return that to our call site global, which is stored in output.
And we can pop Fibonacci 4 off the call stack. And we have gotten our answer. Y'all, come on, let's hear it for Ryan.
Yikes. That is insane.
Okay. Alex, are you ready to do Fibonacci 9?
No, I'm not ready.
All right, we're gonna let it slide this time. Let's talk about what happened. What happened with the call stack here? What happened with these stack frames? Like, what's going on here? Jeffrey, you got a question?
Yeah. What exactly is 3?
3.
I know that sounds crazy, but like, what did we just find?
3 is the 4th Fibonacci number. So
3. Oh,
the 4th number in the sequence is 3.
Got it.
And that's what that is. So
I lost track from the.
Yeah, no, trust me, I understand. Trust me, I understand. Darius, what do you think? You're muted, bud.
Oh, sorry about that. So going through this type of thing like Fibonacci, I was wondering, this is like really good to use for like closures, right? You're doing closure, you just one-time thing. You can like then declare a new function, add on to it. Would that be a good use for it?
Did you come to my closures workshop last Thursday, Darius?
No, I did no, I did. Yes, I was in your closure for. Yeah, I was. You're right.
So those of you that were here, I alluded to something that we were going to talk about at the end of our recursion workshop this week. And this is solving the problem that I think Darius was just trying to give away the answer to, which you are correct, Darius. This is a way that we can solve this problem. But the problem is we calculated Fibonacci 2 twice. We calculated Fibonacci 0 twice. We calculated Fibonacci 1 3 times. That seems inefficient. Wouldn't it be nice if we could just remember Or like, I already did, you already calculated that once. Why are you going to make me do it all over again? Well, the way JavaScript works, once we garbage collect an execution context, that variable is gone and lost forever. So we don't have a way of doing that. But my challenge to you, and Henry, I'm going to take your question. My challenge to all of you is, if you want to take a stab at refactoring this Fibonacci function, one of the ways that you can do that is using closure. It's not the only way, but it is a way that you can do that. If you want to Slack your code to me on our CSX Slack, again, my name is Kyle Combs. You can find me easily on CSX Slack, whether it's tomorrow, next week, anytime you want to send me your version of the Fibonacci function optimized in such a way that we don't have to calculate. Anytime we calculate something, we can save that value somehow and not need to calculate it again, but use the value that we've kind of saved up in our memory to do so. There's several ways that you can do this. I can think of 3 or 4 different ways that you could solve this problem in the optimized manner so that you would not have to do this. But something interesting about a tree recursion like this, if you wanted to calculate the Fibonacci number for 45, your computer would either not give you an answer or it would take over a minute to calculate. And you might think like 45 seems like a pretty small number, but what's happening here, right? We were just trying to calculate the 4th Fibonacci number and it took 10 stack frames to do so. Let's look at why we call this a tree recursion really quick. Henry, do you want to ask your question while I draw this out?
Oh, I was gonna, yeah, you kind of asked us like what's going on in the Fibonacci sequence function, and I wanted to pitch in for an answer. So
yeah, go for it.
Well, at each iteration of the function invocation, you're returning 2 of the same function invocation, so that each time you invoke, it kind of branches out binarily, so into 2 directions, and then that splits out into 2 directions and go so on and so forth until it reaches the base case. And in terms of the Fibonacci of 45, I would go on to guess as the size of n increases, then because you have to split it twice every time n increases by 1, so I guess like the computation time would increase by 2 to the nth power, maybe?
You are 100% correct. That is that is the time complexity of this. So if you're thinking about time complexity, it is that. Again, I don't want to dive too much so people are like, oh, what does that mean to the end? This is a very terribly not very time complexity efficient way of solving this problem. And as Henry was saying, these kind of like branch, right? Every time we run it, we're like branching out. This is what I want to draw out right now, so we can kind of like get a better understanding of why this is called a tree recursion, right? So we calculated Fibonacci 4, right? So Fibonacci 4 is Fibonacci 3 plus Fibonacci 2. Okay. Fibonacci 3 is Fibonacci 2 plus Fibonacci 1. Fibonacci 2 over here is Fibonacci 1 plus Fibonacci 0. Over here, Fibonacci 2 is also Fibonacci 1 plus Fibonacci 0. And we know our base case, we have 2 base cases. So this is 1, this is 0, this is 1, 1, and 0. Now, if I want to calculate Fibonacci 5, give me a second. I did the wrong thing. 1 second. If I want to calculate Fibonacci 5, I'm going to have to Fibonacci 5 is, if we kind of draw these out, we can kind of see what I was trying to allude to about it. Branches, as Henry said. Each time we split off, it's like a new branch. So if I calculate Fibonacci 5, it's Fibonacci 4 plus Fibonacci 3. Well, let's see if I can successfully nab this. And if we went to Fibonacci 6, it would have to calculate all of Fibonacci 5 and then go on to Fibonacci 4. And the problem here is that just like before, where we have a mathematical calculation, we can't move on until we finish calculating that mathematical calculation. The way that we've written this function, I can't move on to Fibonacci n minus 2 until I've finished calculating Fibonacci n minus 1. So JavaScript can only do one thing at a time. Remember, so first I've got to calculate Fibonacci n minus 1. So here in my tree, if I want to know Fibonacci 4, I've got to do all of this before I can move over here and do this. So as you can see, every time we increase n by 1, we are dramatically increasing the number of stack frames that it's going to take in order to get here. So now you can see, if we did Fibonacci 45, exactly how big this freaking tree would be, and your computer, in its infinite power and wisdom, is still going to be like, no, I don't think so. So I challenge you to rewrite Fibonacci in a way that you could calculate any Fibonacci number. And you will know that you have succeeded if you can run Fibonacci 45 or like Fibonacci 100. If you can calculate Fibonacci 100, it'll take a split second to do it if you've done it properly. Otherwise, your computer's just going to freeze, or you're going to get a maximum call stack size exceeded error in your console. So one of those two things will happen. So you'll know you have succeeded when you can actually get a value for running Fibonacci with the argument of 100 passed in. So I challenge you to do that. As Darius so eloquently alluded to there, there's a way of doing it using Clojure, what we talked about last week. If you're not familiar with Clojure, check out we've got a recording of that on YouTube, or you can check out Front End Masters, kind of learn a little bit about that. I'm not going to tell you what aspect of Clojure you can use to do this. We're going to start kind of using that analytical problem solving to use multiple tools to solve problems, because that's what we do as software engineers. So whenever you have something, send it to me, and I will be happy to kind of go back and forth with you and talk through, give you some feedback on that solution. We can talk about ways of making it even more efficient, more optimized. So I'm not giving you carte blanche to just send me all of your code samples. Only optimized Fibonacci sequence. I will give you one-on-one personal review for that. If it's tomorrow, cool. If you send it to me on the weekend, you will not hear from me until next week. But I promise you, I will get back to you, and I will get you some feedback, and we'll talk back and forth, because I want you to kind of like start piecing these things together. So maybe that's what you work on tonight. Maybe you're like, you know what? That's a little, I need to first understand what's happening with recursion. So I encourage you to jump into, I don't have it here. I thought I had a slide for it. csx.codesmith.io. And there is a whole unit with like 15 or 20 practice problems for recursion. Do yourself a favor. Start with the first one. It's the easiest one. They get a little bit harder each time. Try and solve a recursion problem before you shut your computer down tonight. Use what we've talked about tonight and get those fingers clicking. It's just like learning anything, right? If you like watch YouTube videos, you could watch me talk about how to play a song on the guitar for 3.5 hours, but if you never actually grab a guitar and try and play it, it's not going to work. It's the same exact thing with code. We can talk about recursion. You could come and watch this workshop 10 times, but if you never actually try and use recursion to solve a problem, you're never going to understand it. You're going to have to get through that block-driven development. And I promise you, as you do, this will all start to come together, and you will have that moment when it clicks and you're like, oh my God, this is what Kyle was talking about. It just clicked. I get it now. I promise you, it might happen today. It might happen a month from now, but I promise you there will be a time, if you keep at it, where solving a problem with recursion becomes just as intuitive to you as solving a problem with a while loop or a for loop. That may seem crazy to you right now, but I promise you it's on the horizon. So y'all have a wonderful night, and thanks for hanging and chatting about recursion. We'll see you next time.